So we're looking at the different types of circuits. So this circuit I call a basic circuit, and we're definitely going to have these circuits in programmable controllers. So if you've had DC, of course DC is not required for this class, you learn 3 different types of ways that we could hook load to the circuit. Anybody know what those are? Series, parallel, series, parallel.
Combination.
Yeah. Well, the basic circuit is basically, it's a series circuit, but I just want to make sure you understand the difference. A basic circuit is a circuit with only one load. So we have a voltage source, which provides a difference in potential. Then we have our conductors, and then we have the load that's actually doing the work. So we will have these circuits in PLC logic, and also in relay logic. So if you take motor controls, you'll find out that this would be one of the circuits that's legal. So even in motor controls, we don't have multi-load series circuits, and we don't have series parallel circuits. Some of y'all had that. So this guy right here, this is a series circuit. All the resistors are connected one after the other. The advantage of this, of course, we use it for a lot of things, guys, in electronics, electronic devices like diodes and transistors. These guys operate off of, to make them work, we have to put DC voltages on them. In solid state, we call these bias voltages, and these are going to be series circuits. And what we can do with a series circuit is we can set up a voltage at a certain point, right? Y'all understand that? So you'll definitely use these in electronics. Also, y'all probably run into series circuits if you put up Christmas lights. At Christmas, those are series parallel circuits. Used to be they were series circuits. And what used to happen, if you lost one, this is the big disadvantage, if you lose one bulb, you lose the what? You use the whole string. But now most of your lights are series parallel, so now if you lose a light, you lose maybe 12 lights, right? And you still have the rest of them. So that's one problem. And what's nice about that is that you got them across 120 volts. Instead of every light bulb being rated at 120 volts, they're only rated at 10 volts. So the bulbs, if you try to put 120 volts across them, they would pop. So the voltage is lower per bulb, which makes them a little safer. So that's where you'll run into series circuits. We don't have those in PLC logic, and we don't have those in motor controls. So these are series circuits. So the voltage, when we put current through a load, it drops a voltage, and then so you'll have less push after each one of these loads. And how much they actually drop depends on how much opposition each load has. So in a series circuit that you see in light bulbs, all the lights have exactly the same resistance, so they'll drop the same amount of voltage across them. A load. That light right there is a load.
Okay, so it's got something that the energy comes out of.
It takes electrical current and converts it into something else. It either converts it into light or it converts it into heat. You got an electric heater, right? You understand? So your phone right now is a load to that battery pack right there. Right? So you have, right now, you have this basic circuit. You have that basic circuit right there. So my little charging pack is this guy right here, and your phone is the one, is the load. So every circuit has a load. So the load is what takes this current that we talked about and converts it over to work. So the current, a load could be a motor. So when you put that current through a motor, what does it do? It spins, right? You understand? You got a doorbell on your house. Well, the bell would be the what? Would be the load. Yeah. And we can take this. So a lot of the circuits are like this. Now this circuit is not like that, because if this circuit was like that, I would only have one load on this thing. So this is what we call a parallel circuit. So a parallel circuit, what we do is we hook up multiple loads across the same voltage source. So this is the way the lights are wired in here. They're wired like this. This is a parallel circuit. Now, so we know right now, if we lose one of these loads, then that's going to open up the path and there's no current flow. So if this load right here opens for some reason, then these two loads right here are not going to work. Because it has to go through. This, it don't have to go through. So what that means, I can come up here and take this load away, and that has absolutely no effect on load 1, 2, and 3. So this is like in your house. If your house is wired in series, you go up there and turn off one light and everything will go out. But so your house is wired in parallel. Okay. So the advantage of parallel is we can add loads and we can take loads away without affecting the other loads in the circuit. Of course, the more loads you put out there, the more power it consumes. So this is why people tell you to turn off your lights, because as you add loads, each current requires a certain amount of load, which means it produces power, and it pulls more power. So what's nice is you can add loads and do all with a parallel circuit. You can add them and take them away without any problems. And we do have these circuits in PLCs, but they're going to be programmed, right? So pretty cool. And we don't have these circuits right here, but these are predominantly in electronics. And like I said, or you get the Christmas lights or series parallel. So I can lose one load over here. These guys don't work, but the other strings work now. We use series parallel is primarily used in electronic circuits, and they're usually used to set up voltage levels for solid state devices or electronic devices. So we don't have these. We don't have to worry about these in PLC. So which ones we got? We got these single load, single load basic circuit, and then we got the multi-load or parallel circuits, and some control device. So control devices, we use these to control the flow of the current. So I can go over there and so control devices don't do any work. You don't pay power on a light switch. But what it does is it kills the current path, right? You understand? So right over here, my control switch, my light switch is right here. So if I open that up, then there's no current that can get to any of the loads, and all the loads go out. So that's what I have on these right here. So these are parallel. These are all hooked in parallel. So if we was to get up in the roof, we would see it's got a bus running down through there, and every one of them just plug into the same thing. That makes sense? Yeah. So what we do is we add a control device. So we're gonna have these control the flow of current and produce no electrical power. So they shouldn't get hot. If you've got a light switch that's getting hot, guys, you need to fix it, because it shouldn't get hot. It doesn't produce any power. If you got an outlet that gets hot, Scott can tell you this. If you got a outlet that's getting hot, there's something going on there. If you don't know how to change them out, then you need to call an electrician to get that fixed, because those things will cause fires. The connection of control devices does not determine if it's a series parallel circuit. It's how you connect the loads. So we can hook control devices in parallel, we can hook them in series, we can hook them in series parallel. That does not determine what type of circuit you have. So we've got a two-way switch on this thing right here, right? A two-way switch means I can go back and flip it on and turn them on in different ways. It's actually called a three-way switch. We okay? Some of the control devices used in electronics, of course, is we're going to use switches. We're going to use push buttons on our trainers. We'll try to get over there tonight and just look at it. We're going to use sensors. Anybody know what a sensor is?
It's like a sensible.
So we call them senses. What are our senses? It takes physical stimulus and converts it into what? Electrical signals, right? So your brain can process them. So that we do the same thing. We have using electronics. We can develop, they can engineer sensors to sense about anything we need to do in the environment. We can sense temperature, we can sense flow, pressure, force. We can sense presence, whether something's there. We can sense distance, we can sense speed. So in these, we have the ability to input these into our PLC, and then with a program decide what we want to do with those. We're not going to have any sensors on our trainers. We're going to simulate. A lot of sensors just act like these guys right here. Most of our sensors we have, they refer to them as binary sensors. Some people call them digital sensors, which means they're either what? On or off. So, yeah. Yeah, but the sensor itself outputs a digital. It's just like a switch, but instead of being manually controlled, the switch is controlled by something else. And we teach a class called sensors, by the way, which you can take that after you take motor controls. Yeah, they can. So this is an example of a true basic circuit. So what we have is this is a basic circuit. We have our one load. We have our voltage. By the way, this is the symbol for a DC voltage source. A lot of people say it's a symbol for a battery, but it's a symbol for a DC voltage source. So this is a DC power supply. So if I was going to draw the symbol for this thing, I would use that symbol right there. Except the only big thing that I would do is I would come up here and I would put an arrow across it. If you see any electronic symbol that's got an arrow across it, it means it's variable or it means it's adjustable. So it could be electronic, it could be any DC power supply. Originally it was developed because of batteries, because those were the first DC power supplies that we had. Yeah. Well, similar. So if I was to draw your phone, this would be your phone over here, and I would use that same symbol right there for that little, even though that is a battery. Control devices, switches, push button, relay contacts, and of course sensors. Converts a physical stimulus into and. It should be and, not and. And I get credit for these. These are my slides, guys. If y'all see any. Of course, y'all never make mistakes, do y'all? So these are some examples of push buttons. We use a lot of push buttons in industry. We don't like these little toggle switches. One thing we don't like them is they're easy to accidentally trip. So what we do is we usually use push buttons.
Don't call it e-stop.
Well, yeah, they could be e-stops. Normally, if it's got the mushroom head on the top and it's red, these are e-stops. This is not necessarily an e-stop button. So normally e-stops have a mushroom head on them to make them really easy to see and really easy to hit.
Right.
We have, most of the time in industry, you'll see very few actual switches. You'll see these things they call selector switches. And these are big, and they have detents on them, so they're not, you have to deliberate, and they're not real easy to turn. It's real easy to. And a lot of your push buttons will actually be within a safety ring around here. So you literally have to push them. And why they're going to be, we want them to be pretty big is because a lot of people that work wears gloves, right?
Yeah. That's how you can stop the off the button.
Electronic sensors, we have, these fall into two categories, and we have a whole lecture on these. We have what we call contact sensors. These guys have to make physical contact with what they're trying to measure. So maybe a temperature sensor might have to be a contact sensor, right? You understand? Then we have non-contact sensors. These do not have to make physical contact with what they're trying to measure. Generically, these are put under the term of proximity sensors over time, even though a lot of those sensors, proximity means trying to find out when something's at a certain location. Well, a lot of our contact sensors do exactly that, but we don't call them that. So over time, what has happened is the term proximity sensor, now, if you talk to just about anybody, this is going to be these non-contact sensors. These are the sensors that don't have to make physical contact with what it's trying to measure. So this is a special contact sensor. This guy's been around since Methuselah. These guys these are workhorses. They're very simple. They come into different categories. They have big ones like these. These are called pilot duty. Then we have electronic duty, which are real small ones. Which more and more you're going to run into the little tiny ones because these guys can actually run loads. These big limit switches. And when we go over and look at the manufacturing line, we'll see the little micro switch that they have on there. Program controllers don't require a lot of current on their input. It's on the milliamp range, usually around 60 milliamps on the input. So we don't need a big old limit switch with 60 milliamps. So a lot of your limit switches on those guys will be a lot smaller than this. You can see what it does. You can see how it works, right? So how does it work? What it's trying to see if it's in a certain spot, literally comes up and just hits that operator out there, and we have all types of operators that we can look at. So these are limit switches. These are opened up so you can actually see them. And usually we want to open and close the contacts really fast, especially open them up, because that's when we create arcs, and the faster you can open up, the more it will distinguish the arc. What we talk about is people, when you're in a swimming pool, if you take your hands like this and you move them really slow, you create very little turbulence. So if you pull them away real fast, the water rushes in between your hands, right? And so that's why we want a lot of these switches to open real fast. If they open real fast, they do the same thing. They'll suck air through the middle of the contacts and extinguish it off. Now that arc is, I think, around 2,200 degrees, which is hotter than the sun. It will melt stuff, so we want that arc to extinguish extremely fast. Then we have all these electronic sensors. And these guys, this is where we can sense. With these guys, we can sense the distance, we can sense temperature, we can sense speed, we can sense position, we can sense a lot of things with these. And these are really starting to dominate. And these are not contact. So right off the bat, a limit switch is an electromechanical device. And as soon as I say electromechanical, that means that sucker can fail two different ways. It's just like your car. Your car is electromechanical. So your car can fail two different ways, right? It can fail what? Mechanically, or it can fail electrically. Okay, so sooner or later it's going to happen. Everybody here is going to have a flat tire sooner or later. Or a dead battery, right?
Yes.
So a dead battery would be an electrical failure, and then a tire would be a mechanical failure on your car. So these guys don't make physical contact. So what that means is that means that that's one thing you got to not worry about, right? Is their electrical devices only. So these guys can only fail one way. So you're going to run into a lot of these now in automated systems. And we have a whole lecture on this. We'll talk about the different types and what they do, what they sense.
I got a question. Do those also do speed
What's that?
sensors for speed?
Oh yeah, we can sense anything. We can basically, if you can think about it, an engineer's going to come up and design it. Yeah, speed. There's a lot of processes that have to be very, very precisely controlled. We call them closed loop systems, and that's what sensors give us. So what a sensor does, automation, what does automation really mean? Anybody know what that means? Yeah, but what does it mean? Well, it means we're making something with little or no human intervention. So what we do is we create what we call closed loop systems, which means we tell something to do something, and then we use a sensor to see if it did it.
Right.
And so the sensor would be the closed in the loop. So yeah, so if I want to run a motor at a certain speed, I got to have a sensor out there that tells me what speed it's running, right? So like the cruise control of your car, that's a perfect example. That's a closed loop system, right? You're going 60 miles an hour, you engage your cruise control. Well, how in the world does it know your car is going 60 miles an hour? Well, there's a sensor out there, right, sensing the speed of the car, coming back into your fuel control system, deciding how much gas to add to your engine. And it works real well as long as you don't exceed the limits of the cruise control. So yeah, if you go up a big old hill like this, and then it starts shifting down, right? It won't shift down in first gear. and then it'll slow down. Or if you come down a real steep hill and it lets the gas all the way off, then you're dealing with gravity. So within the limits of the sensor system, we can do that. So every closed loop system has limits. So we'll look at this. We got inductive sensors. One of these guys sense. Just metals. They sense metals. Anybody seen one of these lately? I guarantee you ran across an inductive sensor somewhere. This is what's buried in all these red lights out there. It's an that's an inductive sensor, huh? No, that's not a metal strip. It's a loop of wire. You can't see it. Most of the time you can see the loop, and that's all it is. It's an inductive sensor sensing your what? Well, it's sensing your car, and then it comes into the control system, and then decides it knows that there's cars there. We have the passive sensors. These guys can sense about anything. And then over there on the line, we got Hall effect and magneto-resistive sensors. These sense what? Magnetic field. So we use these guys in a lot of speed. We got a motor up here. I need to show. Maybe we'll have time to show it. Photoelectric, we have a lot of these too. We'll show y'all these over there and let you see the difference. And then ultrasonics. These guys, ultrasonics is the ones that's actually sensing speed and position and stuff. Well, I'm sorry, distance. We usually use these to sense distance. Typical loads, lights, relays, solenoids, and small motors. So anybody know what a lights? Everybody's familiar with lights. You know, we need a bunch of lights. We're a visually oriented species, right? See it to believe it. So you're going to run into a lot of visuals out there in the industry. A lot of lights flashing, blinking. Just about every push button you press is going to light up a light on it, indicating that it's also been pressed. Relays. I'll just have to show y'all.
Your relay is in the machine.
What's that?
The relay is in the machine, right?
What do you mean in the machine?
I mean, when it's rotating for the relay.
No, a relay is an electrically controlled switch.
Oh, okay.
So instead of me going over there, so when I turn these lights on over there, who has to turn it on? No, these lights. It's a switch. Relays, I could turn on the lights with electricity. Now, as soon as we say that, we say now we can turn this thing over to automation, because now I can energize and de-energize loads. Right? You understand that? So what we use relays for, we use relays for several different features. Solenoids. Solenoids, all a relay is just a solenoid that's got some contacts attached to it. If you ever played a pinball machine, you run into solenoids. If you've ever been buzzed in through a door, you run into solenoids. If you have an ice maker in your refrigerator, it's controlled by solenoids. If you have a wash machine, the hot and cold water is controlled by solenoids. So you have solenoids all over the place. And of course, small motors. Any large motors, a PLC will not run a small number. And so what we do is we use these guys right here called relays. So this is a relay. Well, actually, this is a relay. This is something that detects a motor. The problem we have with motors is that motors pull a lot of current when you first call it the starting current. And find that out. So on the nameplate of the motor, it'll have an operational voltage on there, and then it'll have what they call amps. That's how much the motor will draw when it's running at rated speed. Rule of thumb is that if you looked at that amps on there, when you start that motor up, it pulls about 6 to 8 times what that thing says when you try to start it. It's just like your car. So you're sitting at a red light and you start off, what do you have to do with your gas? You have to push it down. Then when your car gets running, so you add a lot of energy in there, right? And then what do you do right off the bat? Then you actually automatically, most people don't even think about it anymore. So you have to give it more gas to get it started and moving. than you have to do to get it when it's in motion. So the problem we have is that when we come up with these fuses and these circuit breakers, they have to let the motor start. So they have to let that 6 to 8 times run through. Well, if the motor don't start, and the circuit breaker would never pop because the motor would just sit there and pull the starting current all the time. Or if the motor stalled, it would sit there and burn up. So we had to come up with some method where we could sense overcurrent over a certain amount of time. And on motors, we call these overloads. So that thing on the bottom that you see up at the top, the gray box, that's the actual relay. And then down below that is the overloads. So that way, if the motor does stall or if the motor don't stop, it'll kick the circuit out over time. And so we can run real small motors off the actual relay logic, but most of the time, what we actually do is we use a relay, pull in a relay magnetically, and then let it go that way. Yeah, we can run those little small motors like that. Those run directly. Hand drills, they run directly. Your motor in your refrigerator don't, or your compressor don't. It probably has to go through a relay. Yeah, this right here, we run that. That motor right there, even though it's kind of misleading, that motor's got a brake on the back of it, so it's not as big as it did. I think that's a 1/2 horsepower motor, and we would run that through a relay. We wouldn't run that directly off the line. And then plus, we'll talk a little bit. That's a 3-phase motor. The controls are single phase, so you'd have to use a relay to do that. So lights, everybody okay on lights? I don't know if I've got this or not. If not, I will show y'all a solenoid. I mean, y'all seen solenoids before. So this is basically a solenoid right here. So what we do is we have these things called electromagnets. I think let me fire my camera. Let me see if my power supplies are plugged in. No. Got to figure out what's plugged into what. Oh, here's plug. So anytime we put current through a conductor, it creates a magnetic field. And then we can use metals to concentrate the magnetic field. So this is an electromagnet. I just made this out of a screw. It uses a special wire called, I'll pass it around. Let me see if it's back around. Give it back to me. First of all, we have to use a special wire called magnetic wire. Magnetic wire, it has a really, really thin insulation on it because what we're trying to do is we're trying to get really good coupling between the conductors, and the wires have to be wound very tight. And then normally we put it around a piece of metal to concentrate the magnetic field. Yeah, the screw is acting like the core. And so what it's doing, it's concentrating the magnetic field. And I'll show you what a solenoid. Oops. Let's see if this is going to work. Let's see. Don't want that power supply. Something wrong with that power. Y'all see it smoking?
Power supply,
Yeah. Yeah, it's smoking. Or I guess it might be vaping now, right?
yeah, right. You know,
Y'all know that stuff is just as bad, almost as bad. Not quite as bad as smoking, but
I didn't think smoking was that bad, 30 years ago.
Yeah.
It's like, that's what I'm thinking. In 30 years.
yeah, I smoked when I was in the service.
They're gonna be like, okay, these e-cigarettes are.
Yeah, they're already having problems.
Yeah, they don't really know nothing about them.
Yeah, so can y'all see this? Let me get it out here where y'all can see it. So there's my nail. And then I'm gonna come over here and turn the power supply on. Oh, sorry. Well, guys, I don't know what's going on. Make sure they're not touching back there. Well, this worked a while ago. Let's put it over here. No, I got it short. Okay, so yeah, so electromagnet, right? Pretty cool. What we do with a solenoid is so what I have basically the same thing. I have a magnetic wire wrapped around a straw. Okay, and then what I'm gonna do is I'm gonna come over here and take my voltage source. Plus it's I need to twist it a little bit. It's corroded a little bit.
So what's the green one?
It don't make any difference. Polarity doesn't make it much difference on the solenoid. So it might be plus, it might be minus. I don't know. Okay. So we turn it on. It pulls it in. Turn it off. So this is the solenoid. That's all the solenoid is. So what can we do with that linear motion? Well, so a solenoid takes electrical energy and converts it into a linear motion. So this is what's on your ice maker. So when you go up there and hit the button on the front, or I'm sorry, when it needs ice, it'll automatically turn it on. Your washing machine, hot and cold, that's what it's putting the plunger down in there to turn the water off, pulls the plunger up to turn the water on. So now we can control that. If you're ever someplace where they have to buzz you in, it's with a what? A solenoid. Yeah. It only does it in one direction, so we have to have something else that brings it back. Here I was using gravity, right? You understand? We could have a spring. A lot of your solenoids have a spring on them. So you pull it in and then the spring will make it pop back. Well, there's not a solenoid on your door locks in your car. I mean, why is that? Because all you'd have to do was, as soon as you locked them, they would unlock, right? So it's got a little motor in there. So what we do with the relays, we take the solenoid action and then we make it change switches. So instead of me going out there and changing the switches, then what we do is we connect, no, I didn't want to do that. We connect the switches to that armature or that plunger of the solenoid. Now all of a sudden we got a relay. And these relays come in all shapes and sizes. And we got all kind of advantages from a relay. First of all, what's energizing the thing? We call it energized. So we call this the coil. And then we refer to these as contacts. So you can see what's happened. This is nothing but basically a solenoid. We put power on it, creates a magnetic field, moves this thing, and causes these contacts right here to change place. What's nice though is the coil could be designed to run off DC, but the contacts could be switching AC. Right? You understand that? Or I could have an AC coil switching DC, right? You understand? Or I could have 24 volts DC on my coil, and I could be switching 120 volts AC on my contacts. So that's one big advantage is what the voltage we put across the coil does not have to be the voltage that the contacts are switching. Well, first of all, I can take 120 volts right there, and I can pick up that relay and turn it into two, and the contacts are connected to three-phase 208. All right. I could take the output of my PLC, I could run it at 26 volts, which is well within the limits of safety, and then it could be switching 6,000 volts on the other side on the contacts. I could have 100 watts over here, and those contacts could be switching 5,000 watts, right? You understand? Because of the relay. So most of your high-powered loads are going to be run by relays, guys. So PLCs did not do away with relays. PLCs, programmable logic controllers, cannot output or control a lot of current. But they put out enough to bring in a pretty good relay, about 2 amps worth of current. That's the rule of thumb. You need to actually look it up on the spec sheet to tell you how much it puts out. 2 amps can pull in a pretty good sized relay. And plus, what we do is, well, these big power relays, we can output. So used to, anybody heard of the NEC, National Electrical Code? Yeah. What is the National Electrical Code? What is it dealing with? No, not all safety. The safety installation of equipment. That's what NEC, NAFTA 70 is the safety installation of equipment. Just equipment. It covers keeping things from catching on fire. Now, most of the time it will make you safe. So what they realized is there was no standard on making you safe. So what they came out with is National Fire Protection Association came out with which they call the 70E. That protects you from electrical shock. People say electrocution, but it protects you from electrical shock, because if you don't get shocked, you won't get electrocuted, right? You don't understand that. And it covers preventing arc blasts, what we call arc blasts and arc flashes. You get these high energy circuits, and you have a short across there, and you have an instant current, it's going to blow stuff up, guys. And protecting you from what they call an arc flash, which would be if you've seen a welder, you're seeing arc flashes. You're creating arc flashes. Puts out a lot of energy, right? But those are controlled. You get a big switch gear that something goes wrong and it'll blow up. And then it's outputting these melted, and it's about 3,200 degrees. Metals mount around 2,000 degrees. So all your metals are going to, they're going to melt. It creates a flash, a big blast. All these metals are coming straight at you. And when something hits you, what do you have a tendency to do? Right? So it covers all of it. So depending on the amount of energy you have when you have these arc flashes, that's what 70E covers. So 70E is your protection. 70, NAFTA 70, which is the National Electrical Code, protects equipment. But if you do it right, if you wire it right, then odds are that's going to protect you too. That's what they realize. So NAFTA, I've heard 70E, I've heard 70E. You know, if you get in the industry, you're going to hear about 70E.
I know a lot of machines and equipment are now being manufactured with, the arc safety.
Yeah, arc safety, and then suppose if you got a high energy cabinet, you're supposed to tape it off and say what zones you're supposed to be in.
All residential.
Yeah. And then these guys, the cabinets, you'll probably have to do 2 or 3 things to get into them. I've seen some down at Bros. They had to have 2 keys, and then they had to click a safety on it to actually open the cabinet up to see what was in there. Yeah, so most people think the 70, the NEC is your safety. It's not. It's how to install electrical equipment safely. Okay. So that's why they came out with the 70E. So these guys here can have multiple contacts. This guy here's got 1, 2, 3, 4, 5, 6, 7 contacts in it. Some of them are mechanically connected. It depends on the relay. And we'll talk about single pole, double throw, and that kind of stuff. So normally, what we'll do, if we're going to generate an output from our programmable controller, that output will pick up a relay, and the relay usually runs away. Are we okay? Any questions? So there are some examples. By the way, this is actually off a washing machine. So it has two solenoids on it. One of them turns the hot water off and on, and one of them turns the cold water off and on. Yeah, this is a directional control valve. Directional control valves, what we're doing is we're using solenoids to control fluid pressure. So pneumatics or hydraulics. Yeah. And what's nice about the solenoid is we can shift the solenoid either way to control which way the air flows or the fluid or the gas or the liquid flows. We can do it electrically, and as soon as we say electrically, we mean we can turn it over to relays or we can turn it over to programmable logic controllers. This is just a valve. This is a solenoid that comes off a pinball machine. Anybody that's played pinball, all those things that hit that little wiper, those are all solenoids under there. So usually they got a little rack and pinion where the solenoid generates this and it causes this to push and causes it.
Yeah, when you push that, that's the relay, right?
No, that's the solenoid that's actually causing it to move. Solenoids don't usually require a lot of pressure, so odds are it's not going through a relay. If it was, most relays you can actually hear them click when they energize. That is just a water valve or some type of valve. So water would come in one way and then this would enter. So not a check valve. You know what a check valve is?
Yeah, I know what you.
What's a check valve?
It's one-way flow.
Yeah, one-way flow. Yeah, this is definitely not one-way flow.
Okay.
So you just can't see the threads on the other side. Or anything.
Yeah, okay.
These are relays, guys. We have three categories. We have what we call a control relay. These are what PLCs replace. They replace control relays. We won't have PLCs in motor controls or actual electrical controls. We'll have these things all over the place. These guys are the relays that make decisions. If everything's right, if everything's okay, if all these things in the right way, we'll use a control relay. Then we have power relays. These guys are designed to run heavy loads. This is called a contactor, a magnetic contactor. This is called a motor starter because it has these, we call them overloads. Those are the devices that sense when the motor don't start or if the motor stalls. And these are called magnetic motor starters. So you can have a contactor running a motor. Some of your small motors, like the motors in your house, the overloads are built into the motor. And those are usually thermal overloads, guys. You need to do thermal overloads. They use just a bimetallic strip and they reset automatically. So if you get somebody out there working on your air conditioner and that motor stalls, if you're going to work on it, you need to make sure you remove power, because what happens when that overload cools down, what's going to happen? That motor's going to take off. Industrial overloads don't do that on them. In fact, industrial overloads has a reset on them that you actually have to reset it. You can see it real good on this one. That's a big white handle sticking out right here. So I literally would have to come in and press that to reset those overloads before the motor would come up and run again. In industry, we don't want motors just to take off by themselves.
You said reset the overload?
Yeah, resets the overload.
Okay.
Huh? We're talking about an overload condition. So like we said, at your house has got relays. If you went out there and just open up the panel on your HVA system, if you got an outside unit, you'd see relays on there that turns the compressor on, that changes the speed between high speed and low speed, or medium speed and low speed for heat and cooling. You'd see that. Sometimes they got special motors now, but we're not going to talk about that. And those motors have internal overloads. They're inside. In fact, you can actually see it on this one. This is the actual, we call it the stator, the stationary section of the motor. This is a 3-speed motor. And, I'll pass this around, let you look at it. So This is the actual overload right here. It's actually built into this. So, but this is a little thermal strip, and the way these things work is they'll kick off, and then when they cool off, what will they do? They'll reset. Yeah, automatically. So most of your real small motors, your fractional horsepower motors, they'll have internal relays on them. Any motor that has the ability to be wired for different voltages will have external relays. So we call this a stator. This is the actual stator. This is the frame. How do you get the name stator? Because this is the part that don't move. This is stationary. And guess what we call the part that spins? The rotor. So all I'm saying is when you're out there, if you got one of the motors on one of your systems is not working or it keeps stopping, you don't need to get out there and start pulling that thing off without killing power out there. Because that thing will take off on you. Right. If it don't have these overloads on the relay, then they have internal overloads. So you can actually see these. Sometimes they're electronic. This uses heater elements. So how much they have very low resistance, but they create heat. And the more current flow you put through them, the hotter they get. So they work off heat, thermal overloads. Yeah. So what you'd have to do on these is if you hook the motor starter up to a different motor, you might have to change out the actual sensors. Solid state usually has a little dial on it, and this gets us in trouble too. Anytime we got something that a guy can turn, and unfortunately, guys, it's kind of built into the. So anybody tell you that men are basically, there's a lot of things different. So a lady, what a woman will do, she will ask somebody what a switch will do. What will a guy do? He'll go over and flip it and see what it does. Every time. Yeah, every time. Every time. So a guy called Stephen Wright, I don't know if you ever, he had a real dry sense of humor kind of thing.
The relay is that chip, right?
No, that's not a relay. A relay is a big old thing. That is the thermal overload. That is the overload that kicks that motor out if it don't start or if something happens and it stalls. Yeah. Yeah. So like if you don't ever change out the filter on your air conditioner, sooner or later that motor's going to overload. But you don't want the that's the contactor, but the overload's down below that. That's an electronic overload. And the problem we have there is it's got a little old tiny knob that the person can adjust depending on what overload is required by the motor. Well, they have that because it's solid state. These over here, if you hook it up to a different motor, you literally have to do what? You have to change those heaters out. That thing right there, you can turn a knob. So what happens on those is that a motor will start kicking an overload, and the guy goes out there and turns the thing up, and it stops kicking the overload again. And then eventually it burns out that $5,000 motor out there. Yeah, solid state. Yeah, those are solid state overloads. So the heaters are better in that the person has to mechanically change them out, right? You understand? Those the guy can do turn it. These are all different types of motors, guys. Usually energized through a what? A relay. So I could literally run this guy right here, not from a programmable controller, but the programmable controller could pick up a relay, and the relay can run the motor. Yeah, this is a relay. They're gonna be pretty good size. This is a. Let's go look for a controller there. I'll take a 10-minute break. My boss is calling. That's a good time, right? Yes, ma'am. So we use symbols. We use a lot of symbols. When you go out and buy a new TV or something, it comes up with what we call a pictorial drawing. Pictorial drawing is where they actually draw your TV, and then they'll draw pictures of DVDs and all this other kind of stuff to show you how it hooks up. Those take up a lot of room. So what we do in our trade, of course, is we have symbols. If you was to build a house, they're not going to have a drawing of the house. They're going to have a drawing using symbols, right? You understand? If you wire electrical houses, they're going to have a drawing using symbols that the electrician uses to know how to wire the house. So these are some of the symbols of our trade. So at the top, this is a circuit breaker. So we have circuit breakers. We call these overcurrent protection devices. These are hooked in series, so all the current has to flow through them. We have fuses and circuit breakers. What advantage does a fuse have over a circuit breaker? Well, normally the main thing that these things is they don't sense a voltage, they sense a current. The current's what burns wires up. So there's no conductor that is rated in a voltage. All your conductors are rated in what we call an ampacity. What's rated at a voltage is the insulator that you put around that conductor. That insulator that's trying to keep that push in, right? You understand? Those are rated in voltage. So insulators are rated in voltage, but conductors are rated in current, right? You understand? Current is what the current flowing. We know that what does work equal to? Let's see if I can do this. Anybody know what the formula for work is? What's that? Not power. Power is work. Of course, work. We don't rate work in watts. Work is rated in like foot pounds and stuff like that, right? So what we do to get work, to do actually work, 4 times distance, yeah. If I can get this thing to work, yeah. Equals force times distance. Now, what we're doing is we're calculating power. Power is equal to how much voltage is pushing the current. Yeah, it's V times I. If I can get my thing to work. Times I. So a circuit breaker is not rated in, it's rated in volts. Now the voltage rating, it says how much push it can break. So normally our house breakers are going to be rated at 250 volts because the maximum voltage we have is 240. Right? You understand that? That means, okay, I've got all this push out there pushing that current. When a circuit opens, that push is still there. How much push can that contact break? Right. So usually contacts on relays are rated not only on current, they're rated on how much voltage they can actually break. So a fuse is rated in 2 things. A fuse is rated in how much current is going to require to blow the fuse, and then how much voltage it guarantees it can keep from arcing through the fuse. 30, but you'll also look, it'll say 250 volts. If you look at the cap, it'll give you the voltage rating. Now the voltage rating says, okay, I've got 250 volts out there pushing this current. And when it breaks, it's going to create an arc. When it creates an arc, it's going to create ozone. Ozone has a path. How far will it break to prevent that from pushing over there? And lightning is a perfect example. We've seen shorts that exceed that, and they just keep jumping over, right? Even though the contact's open, if it jumps across the contact. So the big advantage of fuses is they're cheap per amp. So in industry, guys, you're still going to run into a lot of fuses. In houses, you're going to run into a lot of circuit breakers. What advantage does a circuit breaker have over a fuse? You can reset it, yeah. But you go down to Lowe's and look at a 15 amp fuse, and you look at a 15 amp circuit breaker and look at the difference in those prices. We're talking one is $20 and the other one is less than $1. Right. People say, well, if it keeps blowing, I said, well, if you have a fuse that's keeping blowing, you don't need to keep replacing that fuse. You need to figure out why it's blowing, right? So industry is going to have a lot of fuses because of what? Because they're cheap. A lot of the fuses actually have replaceable filaments in them. So you unscrew the caps, you put a new filament in, yeah. So I think we might have one over here. So that's a fuse. This is a symbol for, I don't even have a symbol for a fuse. Anybody know the symbol for a fuse?
That's all the rules.
Doing the
The-
break.
Yeah, you use continuity or you, anybody know the symbol for a fuse? It's just a little squiggly line. Yeah, if I, I'm probably gonna have to start using, this is my new computer. I'm probably gonna have to go back to my old one. This guy don't want me to write. Yeah, that's a symbol for a fuse. Just a little thing like that. Yeah, usually we bring the lines in. Yeah, we bring the lines in and then the fuse comes up here and just goes, yeah, it just goes between the lines if I can do that. This is the symbol of a relay coil. So it's just a little circle, got two lines coming into it. We're going to use this symbol a lot. Alan, the PLCs for Siemens actually draws a circle. The Allen Bradley came up through old school stuff, and they used two parentheses for the coil. This is the symbol for contacts. These are usually for a coil. So what we're going to do is we're going to give the relay a name. And I'm just going to, just for example, I'm just going to put a name up here. I need to do something. And then all the contacts that's controlled by that relay, we give them the same name. And here we'll call them symbols. Here, this class, symbols are optional. The version of programming we're using, we're using an older version of, but it's still very, very popular because a lot of them up there, we're using something called RSLogic 500. And why we're still using that is because these are the PLCs we have. The new version of Allen Bradley programming software is called, it originally went to what they call RSLogic 5000, but now they call it Studio 5000. And I'll pop that up and I'll show you how easy it is. And what I learned, so I started programming computers. I did it in a language called machine language, which is a binary language. Then we moved to assembly language. Well, if you understood machine language, assembly language was nothing. Then we came out with a language called BASIC, which was the programming language for years. If you knew assembly language, you could adopt over. What you're going to find out, guys, is once you do this, it's one of the, and the analogy I use is that it's like when you get a brand new car. You know that car does the same thing as your other car does. It's just that you have to figure out how to program the radio. You have to figure this out. And you have to figure out where the wipers are, right? I had problems with my wife's van. I drive my car. I got a little HHR that I've been driving for years. And she's got a town and country. We're going to have to get one of them now. She wants a new one now because all our grandkids are grown up and they're driving. So we used to be the haulers. You know. But when I get in there, started raining, I couldn't figure out how to turn on the windshield wipers. So once you learn how to drive one car, you know it basically does the same thing. And it's just, okay, this is how they do it. It's just like programming robots, guys. We got 4 robots over there, and if you take the operation and programming class, you're going to be assigned to one of them. But what you'll find out is once you learn how to program one, they all do the same thing. It's just the instructions are basically a little different. So in the 2 symbols they don't show y'all is we're going to use, as we have a circle. If I can draw, if they'll draw for me. Yeah, I'm gonna have to go back to we got a circle. And we got a little squiggly line in it, if I can draw it. Might have to draw it on the board. I'm gonna have to. I'll go back to my other computer. Not here. I don't have it over here, guys. So what we got is we got a circle, and then we got a little squiggly line in the center of it. I can see if I can do it with my mouse. It looks kind of like a fuse. This is a symbol for an AC voltage source. Not bad for a mouse. And then we got this symbol right here. This is a symbol for a DC voltage source, right? This short line, this represents the plus polarity, and then the long line represents the positive polarity. And this is a DC voltage source. And we're going to be using these, and we'll show y'all why when we get in there. We're not going to actually do any wiring of the PLCs this semester, mechanical, physically wiring the PLC in this class, but you're going to have to draw how you would wire the circuit up. We don't do it in advanced, we do it in PLC 3. So if you take the third PLC class, you'll be mounting the PLCs on these units right here. In fact, what we do in this class, in intro, because we just don't have much time, in intro to PLCs, like we said, we'll get into all the way up to counters and timers. And then after that, we'll get into the stuff that we can do with a computer, right? You understand? And we're going to use the Allen Bradley PLCs because this is still the predominant PLC in the United States. The predominant PLC over in Europe and in Germany is made in Germany. It's called Siemens. What has happened to us is that we're getting a lot of German companies moving into our service area. And most of those are going to Siemens PLCs. So if you went to Brose, Siemens PLCs. Gas Pump, I'm not sure. I think Flexingate still uses Allen Bradley's. They're tier 1. So what we do in the PLC 3, or what we call PLCs in automated systems, is you literally convert our Fisto line from Allen Bradley's over to Siemens PLCs, and you wire the PLC and everything. So it's a really good course, and we've only taught it. This will be our third time to teach it. This is a course that we're developing for the state. Nobody in the state does this yet. Huh? This right here? Right here. PLC 3. What we call PLC 3 is actually called ILT.
198?
No, 212, I think.
Oh.
Huh? We offer it every summer during the day. And you can take it after this class, by the way. You don't have to have the advanced PLCs to take it. So what we do is we teach you how to take the programs that's written under RS Logic 500 and adapt them over to what they call Step 7. They call it a TIA portal, the newest version. So we have light bulbs. We have push buttons. Normally that's a symbol for what we call a momentary contact push button. Y'all know what those are? Yes, no? A momentary contact. So these are momentary contact push buttons.
Yes, it's going up.
So what I have to do is I come over here, when I press it, it makes a circuit that says on there. This would be what we call a normally open. So right now, this would be an open circuit. This is a normally closed.
Then it makes contacts
In the stop button. So this one, if I was to check between 9 and 10 right now with an ohm meter, it would measure 0 ohms. This right here would measure infinite ohms or overload. When I press this one, it would make a contact. So right now, if I hooked up a light to this one, it would be on. As soon as I put the power on. If I hooked the light up to this one, it would be off. Because this is normally closed and this is normally open. That makes sense?
Yes.
Well, like, where would you see one of those at?
What this?
Yeah.
Normally closed, we usually use these we use them for a lot, but normally we use this for a stop button. Why we use a normally closed for a stop button, which would be this symbol right here. So the symbol, notice it's got the terminals where we make connections to it. But one of them, the symbol for the push button is drawn above the line. The other one is drawn below the line. This one you see, I have to press to complete the circuit. The other one I have to press to break the circuit. Okay. Normally what we want to do is that, and this will show up in PLC, so if, let's see if I can draw this. I might have to draw it on the board. So normally if I want to run, and this is a perfect circuit right here. In fact, this is the one I'm going to use. So this is the next thing we're going to get into, and this is the name of the game, guys. This is what we call a ladder diagram. Can you see why it's called a ladder diagram? Because it looks like a what? Ladder. What we do is these are our two power leads. These are our two lines, right? So we have two, we call them L1 and L2. And then we connect circuits between L1 and L2. And they're either going to be parallel circuits or they're going to be series circuits, or basic circuits. So this would be a basic circuit. So, and we're not going to talk about the overload. These are actually the overloads for the motor. So this is actually a motor starter. So we won't talk about why they're over here. We won't have to deal with these inside the PLC. So what happens is they're calling this relay, what's the name of that relay? M. It's just M. It could be, this is just generic. I can show you a print and they would, they usually use like mnemonics or memory joggers, and they'll give it several letters to actually name these things. And then every contact that's controlled by the relay, we give it the same name. Well, this right here is a stop button. So notice it's what? It's normally closed. This right here is normally open. So what happens, and you'll see this a lot in the industry, we'll have a start button and a stop button. You don't have to sit there and hold the start button for the motor to run. Yeah, so what happens is, I'll try to get this. So this is actually a line diagram. So I'm definitely going to go back to my other computer. For one thing, I can't bring up the pen. Let's see if the pen works. Okay, there we go. So right now, you know, I have energy. If this will draw, it's coming up here, goes to the stop button, it's sitting right there. And then what happens is I press the start button, just momentary, I have to press it. It comes over here, energizes this relay, right? You understand? Closes this contact right there. So now it's got a secondary path. It can hook that up. And so now I can let go of the start button and the motor sits there and runs. Okay, so how do I stop the button? What do I need to do now? I need to break the circuit. So I'll come over here, press the stop button. It drops this contact out, and now the motor stops. Okay. So that was a perfect example of why we need a normally closed push button. This is called a 3-wire control. This is called a memory circuit. And these are all over the place in the industry. So you'll very seldom see a motor running off a switch. You got a start button. You press it. You hit it. It runs until you hit the wall. Huh? Yeah, you're gonna see this all the time. Yeah, I could go over here. I could go over here at on my roll up. Mine's electric garage doors over there in my other shop. I press this open button. Now what they'll have here is though on a garage door opener they'd have a limit switch. So what happens is when the door gets up to the top, it trips the limit switch and it acts like a stop button. It turns the motor off, and then the reverse circuit would be the same thing. So if you got an electric garage door opener, you probably need this. A lot of times now, instead of having limit switches, they'll use optical. Yeah, but it works the same way. So there's your stop button. So what if that stop button was a normally open button? Well, you'd have to press the stop button and hold it down and hit the start button, and somebody's going to have to sit there and hold the stop button at all times. Yeah, we're going to pick it up. So and then, so the way this works is if I don't press the start button, this is a normally open contact being controlled by M. So the light would be on. So this might be up on my panels. The stop button, this light might be inside the stop button, right? You understand? And it's lit telling me that motor's not out there running. So I come over here and press the start button, this contact opens, that light will go off. But I could have another one down here using a normally open contact with another light that it might be labeled run, right? You understand? Now we don't show the motor circuit because the motor is being controlled by a big old relay out there. And it's going to be so most of the time we deal with two circuits and controls. We have a control circuit and then we have a power circuit. The power circuit is in a cabinet that people can't get into. The control circuit is usually real easy to get into. The control voltage now is usually new systems. Old systems, you'll have 120 volts out there. That was just for years. On new systems, it's probably going to be 26 a maximum, maybe 24, usually DC. And why that? Because 70E has said anything over 50 volts is considered to be lethal, and that's where you have to start wiring this high power PPE, personal protection equipment. 24 volts, you can go in there, just standard stuff, whatever your company requires. because it's below that. And then you'll send that 24 volts over to another cabinet, right? You understand? And it'll have a big relay over there, and it'll might be 660 or 240 or 480 or something like that. But it'll be in a cabinet that's all locked up. It takes somebody with a key to get into. So what they don't draw in the control circuit is they don't draw the power circuit. So we would have to look at another diagram. This is even true if you went out and looked at your air conditioner. It's got a diagram out there, and it's got, yeah, it shows you the power circuit, and it shows you the control circuit. So this relay would be over here, if I can draw, guys. Yeah, it would be over here. This one over here, we would draw the power circuit on this one over here. When I hook it up, is we'd come over here. It's 3-phase, and then we'd come into a 3-phase motor. And by the way, these little hooks, by the way, these are the overload sensors. It's not like a fuse. It's actually a hook. It goes like that and like that. So that would be the sensors that's actually sensing that. And all these would be labeled M also. So not only is this contact controlling this, we call this an auxiliary contact. So this right here does not have to be rated at the current and the voltage that your main contact's on. And then these would be your power contacts. And this would be the power circuit over here. So when this relay right here energizes, no longer does it close this and opens this one, it also closes these, but these are going to be where? They're going to be over in the power circuit. Yeah. So this is very, very common. So our PLC, if it needed to bring in a motor starter, the motor starter would actually be on the outside of the PLC, wired up to one of the outputs, which we'll talk about later on. Are we okay? This is ladder diagram. Guess what we call each one of these individual circuits? What do we call the steps of a ladder? Rungs. Yeah. So we call these rungs. These are rungs. If I can get it to draw. Rungs. I'm not going to put it. I could probably try to do it with the mouth. R-U-N-G. So most controls are made out of a bunch of rungs. And that's what this is over here, the next drawing. So this is a typical ladder diagram. Another symbol they didn't show y'all is this symbol right here. This is a symbol for a solenoid.
What's the symbol?
This one right here. This is a solenoid. Yeah, one motion, you know. And these are symbols for relay coils. That's all the yellow ones. These are our loads. So this would be a series circuit, right? Basic series circuit. This does not make it a series parallel. These are control devices. So how you could hook the control devices has nothing to do with whether it's what, parallel or series. So there's our load. This is a parallel circuit. So we have parallel circuits, right? You understand? Within this one circuit. So we have in motor controls and in PLCs, we only have two circuits. We have basic circuits or we have parallel circuits. We don't have any multi-load series circuits. Notice me grimace. 5000 has changed the rules a little bit. This class, we have no multi-load series circuits. We have, so only two types of circuits we have. We're going to have parallel circuits and single load series circuits. So this one here has got 1, 2, 3, 4 loads controlling. You can tell it's a motor starter, by the way. So this right here is nothing but a control relay. That's a control relay right there. These are motor starters. We know they're actually magnetic motor starters because they have these symbols on the outside. These are the actual overload contacts. Right. Not the sensors. These are the contacts that would open the circuit. And so here's the sealing circuit that we was talking about. There's the stop button. We got one stop button. Got individual stop buttons on this one, right? You understand? I need to be drawing this because it's not being recorded. We have one stop button. This is the E-stop right here, right? Y'all see that? So it would kill both these motors. And then, of course, then I have individual stop buttons where I can stop each motor individually. We okay? Ladder. This is ladder. We call the way we're going to be able to do logic. We'll look at logic with this. We have different logics we can do. We can have what we call ands, nands, nors, and nots. So a lot of people call this ladder logic. Ladder logic, the logic is actually what's making the decisions on when things happen. It's like this. This is what we call a NOR logic. So NOR logic says this or this will turn the line off. Or turn that load off.
Okay, so both of them can turn
Either one.
either one. Okay.
And that's when we say either or both, or that means we're talking about either an or a nor. Nans and nors will turn the load off. Ands and ors will turn the load on. So notice here I said I can press either one, A or B, to de-energize it, right? So that's the big difference. Yeah, so this is the way it lays up, and this is the way we're gonna draw this, by the way. This is what we do in PLCs. We pull symbols down. We don't draw it, we pull symbols down. So what we'll do is we'll create a new rung, and then we'll bring symbols down that we want to put inside the logic. Make sense? We can't do this inside a PLC, but we could put a output over here that would actually generate an output on one of our output pins, and it could bring in the motor starter. So the motor starter itself would actually be on the outside of the PLC. And we'll show you that. What time is it? What time does class get out? 9:45. Okay, good. What we want to do tonight is we want to go over to H111 and actually look at the PLCs in action. Actually see sensors and see what an automated system looks like to get a little feel of what the PLC does. Like I said, when I worked out at US Steel, everything was done with relay logic. It was really good. But relays are electromechanical devices. So what does that mean? They will fail. They have two reasons. And those suckers, one wall was nothing but relays. And you think about that, it was so important. These rooms were air conditioned. Normally, you don't find very many air conditioning control systems inside there. They had air conditioning inside there. Some of the guys used to come in there and sleep during the summer. So we find mats and stuff in there all the time. They came in there and they replaced half of that with PLC because most of it was decision making. It was just relays that were just in there to make decisions on when things happen. They wasn't handling power. They were just handling decisions. And that's what we replaced with the PLC. We replaced all that decision-making stuff, right? We'll start off with in fact, this class, I'll probably fire this guy here up and just let y'all see the very similar between them. So one of the main languages we program, so originally when we started programming microprocessors, even computers, we used a binary language called machine language. And so we had a binary code, we call them operational codes, that we would put in. And the way the processors work is when you first turn them on, they go into what they call a fetch phase. And the fetch phase, they'll go out and grab it, and they're looking for an instruction or operational code. And then it comes in, and then it switches to the execute phase, and it does what the instruction told it to do. And then when it gets to that, it switches back into the fetch phase. So you have what we call an instruction sheet. I'll try to find one that gives you all the codes for every instruction that processor could do. Then we switched into a language called assembly language. Assembly language was a language where you use little mnemonics. You know what a mnemonic is? A mnemonic is what we call a memory jogger. So anything that you use to try to remember stuff, that's a mnemonic. It starts with an M. It's M-N-E-M-O-N-C, IC. So what we would do is every instruction that was binary over here would have a little mnemonic that would represent the instruction. And then we'd put all kinds of garbage out there telling it additional information. But the problem is the processor has no idea what that is. So we would run it through a machine language program called an assembler, which would take those mnemonics and automatically generate the machine code for us. And then we would send the machine code into the computer. Then they came out with BASIC. Well, BASIC, what it did is it actually changed programming into the English language. So if I wanted something to go to the screen, I would type in print. And then in quotes, I would put there what did I wanted to print, or I could do a variable. But that didn't work. So we had to convert that over to machine language. It uses something called an interpreter. And what it would do is it would have all these machine language little modules over here, and when it saw print, it would cause that module to actually run inside the computer. Then they went to something we call a compiler. A compiler actually takes a high-level language and completely converts it into a binary language of ones and zeros. And that's what we use. That's what PLCs normally use now. It uses a compiler. So what you do is you're going to write your program in a high-level language, which makes sense. So the predominant programming language for PLCs is ladder. So I'll come up here and I'll draw my ladder program, and by George, I will download it into the PLC, and it will compile it. So the PLC has no idea what ladder is. All it knows is ones and zeros. So it uses a compiler. Some of them have a simulator, which I'll show y'all. One's called Logic Pro, which is really neat because you can learn how to do RS Logic 500 without having a PLC. But it uses an interpreter. It never generates a real machine language program. So this is the language we're going to use, guys. We're going to draw these things. Well, we're not going to draw them. We're going to pull symbols in. Yeah, we'll pull symbols in. So we have a symbol for a new rung. So we'll create a new rung. Just pull that symbol down, it'll create a rung, then we'll start populating. And the rung starts out to be a shorted out rung, so it goes directly between L1 and L2. And big E's will pop up here on the left-hand side saying this has got an error. And then we'll start populating the rung. And we'll just pull symbols down from a table into where we want them to go. If we want a down drop, we got a symbol for a down drop. We pull a down drop in, then we pull the symbols into the down. What you're trying to do. So here's our power rails. Source, of course, inside the PLC, it's not actually there, right? You understand, because it's a program. So I'll write our program in a high-level language, but we can program. I'll give you the names. We have different languages that people that came up through different disciplines can program PLC. So they got a language that uses mnemonics, just like assembly. For people who came up through that route, right? You understand? They got a language that's very similar to one of our most popular programming languages now called Pascal. They've got a PLC that we can program some PLCs there. But the ladder is still the most predominant because electricians understand this. They don't understand mnemonics. They don't understand logic. If you came up through digital, we have a programming language that you can program using ands and or symbols. And I'll try to show y'all those too. The only language that RS Logic 500 supports is ladder. And these are all control, right? So we usually, in motor controls, usually L2 would be your considered your common. Over here, this would be considered your electrically hot side. In PLC, this is going to be a little different. Are we okay? And here we have runs. My lines, I must have moved this. My lines don't line up. Extremely important to learn the symbols used in reference to your trade. Now, why we need to do this is that inside the PLC, we're only going to have a very few symbols. The only symbols we're going to use here is normally open, normally closed contact symbols. Y'all know what those are, right? So the normally open contact symbol is nothing but two parallel lines. Then the normally closed has a slash through it. So those two symbols we're going to have to know. The symbol for a coil. Ours is going to be a little different. Inside Allen Bradley, it's going to be two parentheses back to back. It's going to so it's a circle, but you just don't complete it.
Okay.
We don't have any light bulbs inside the PLC. We would hook a light bulb up to one of the outputs. Now this is why you have to learn these symbols, is because every input, when you draw the diagram on how the electrician is supposed to hook up the inputs and the outputs, you have to use these symbols right here. You have to use the electrical symbols. Yeah, NO for normally open and NC for normally closed.
No, the ABB for the coil, is that, ABB relay coil?
What's that?
The PLCs you was talking about.
It's on RS Logic. RS Logic 500 uses the two parentheses for the core.
Is it like what is relay coil?
No, it's just a symbol up there at the top. I don't have it on this computer right now.
No, I've seen it, I use
Yeah.
it for hours.
Yeah.
I know what you're talking about.
Yeah, up it, because you can name the coil anything you want.
Just for reference.
So it's just a symbol for a coil. And like I said, on RS Logic, I'd have to look at 5,000. I got 5,000 too. I'll show you all the similarities and show you how easy, if you learn RS Logic 500, how easy it would be to go to the new version 5,000. And I'll show y'all even the Siemens, the TIA portal, the Step 7, and you'll see, good gracious, it's almost exactly the same. Both of them, all of them that I know of support the ladder logic.
And you said the coil as well, like the LNC are the three main ones we need to
No, and then we're gonna pick up symbols for timers and counters.
And that's the coil is that second to right one. That's the symbol.
Right. Now, but if I was to hook a light bulb up to the output, when I draw that circuit, I would have to use that symbol right there.
They indicate like,
Yeah, the indicator light.
right. 'Cause you don't
If
have-
I hooked up a normally open push button to the input, then when I draw the wiring of my inputs on my PLC, I would have to use the normally open push button symbol. But then we represent it inside the PLC with either normally open or normally closed contact, depending on what type of push button.
The 500 series you was talking about, how far does that go back on this one? Like, when was that introduced, you know?
Good gracious. The first one they came out with, I think, was RS Logic 5.
Okay.
And then 500 changed everything. 500 changed everything.
So is it
And then
going
that
on-
PLC right there changed everything. This is the SLC 500 series PLC. This PLC, that's right here, really changed the way
What series
PLC.
is that?
Yeah. This is a 500. It's called a SLC. I'd have to look up. We call them Slick 500s. It's actually a 504. It's a 500 series, but it runs a 504 processor, which is this guy right here.
The one I work with is like, it's ABB 1305 Series C. It's obsolete now. It's Rockwell Automation.
Yeah, it probably it probably runs on 500.
Yeah.
So there's a ton of PLCs. That's why 500 is still real popular. So even if you bought the new versions of, so when we get our brand new disc in every year, when we got tons of discs, by the way. When we get the new version, every one of them still has RS Logic 500 on it. So there's no telling how many PLCs in the United States are still using 500. 5,000 is the new one. So all their new PLCs have dropped support for 500. So you'd have to go to 5,000. Huh?
A lot of your automation moving towards the 5,000.
The 5,000 are in our area also the Siemens PLCs. And we have a 1214 CPU, and I'll bring one over and show you the similarities. It's and show you the similarities on the steps you go to when you set up a new program. You have to go through a certain steps that we'll learn this semester, but then I'll bring 5,000 in here and you say, well, gosh, the steps are the same, you know. And I'll bring Siemens in and you'll say, well, gosh, the steps are the same, right? So.
They're gonna be similar to the
Well, what's ladder logic? Ladder logic is ladder logic, right? You understand? It's ladder logic. But our new versions are basically use some other symbols. Well, I will look at so when we go into timers, some PLCs still use the coil-based timers. Most of your new PLCs have gone to what we call a block instruction because it's just so much easier to see the information the way you put it in. And like I said, we'll get into timers and counters and stuff. Then we have switches. Normally you don't see. By the way, on a switch we have what we call poles. Poles is the numbers of basically the numbers of positions that control a circuit, and then we have throws. That's the number of positions that will actually control the circuit. Does that make sense? Probably not. Yeah, so your light switch is what? If you went out there and look, most of the time when you look, it just depends. If you looked at the box on a light switch, it's called SP, right? SD. And it would come over here and it would look like this. So this would be, so we got a single switch and it only controls one circuit, right? And so that would be only one pole, and it would only have one throw that controls the circuit or actually powers it up. So some of their switches are wrong, but symbols are not quite right. The other symbol that we would have is we'd have this guy. And so this only has one switch, right? So that would be a single pole, but each switch, I could put it in two positions. So this would be a single pole double throw. If I come over here and do this, and then over here, I come down here below that and do this, and then I put a little dashed line on here, it means they're operated by the same operator. We'll see just one switch. This right here would be a double pole, single throw, right? So we got two switches, but each one of them only control one circuit, right? You understand?
So that would be like a room with two light switches. One on
Well, that's weird. It's kind of a variation of a double pole. Well, no, it is a double pole. It is a single pole double pole. And it's wired really neat. Yeah, so what you do is you bring in your power, if this is L1, and you hook up this. And then you'd use a double pole, if I can draw this. And then you run two light wires over here. Then you'd have another one over here, and it would look like this. And then your light bulb would be over here. Most people call these two-way switches. That's what they call them. Three-way switches.
I don't know why.
It allows you to have two light switches, so I can come back and, yeah, so, and these, if you notice, these switches don't have off and on them. Because what happens, they always have to be opposite of each other. So if they're in the same position, it won't be on, right, if they're in opposite position. So this is a two-way, they call these three-way switches. And it's just nothing but two double pole, single pole double throw switches wired like this.
That's because it's got 3 screws on it.
Yeah, it's got 3 screws. That's exactly right. You're right. That's why they call it. That's why electricians they call it a three-way. Yeah, it's got 4-way. 4-way switches are really 4-way switches are really weird because instead of coming out like this, they actually crisscross. So they're wired. So this would with these three. So they call it 3-way switches because it's got 3 wires that hook up to it. So that's what electricians call this guy. But technically, so it would be what we call single pole double throw. Then we can take this and then I could come down here and put another one of these, right? And then I can put the little dash down on that. So what would this be? It would be a double pole double throw. So this is the way they got that thing drawn. It's really weird. I've never seen it drawn like that before. So that's when they're drawing their switches so they go like that. And this is about as high as you'll see. After that, we'll go to these guys right here. And these are usually referred to as selector switches. So this would be a single pole, 1, 2, 3, 4 throw switch, right? And relays are like that too, by the way. That's the way you buy relays, the number of poles, the number of throws. This is a float switch. This would be, well, this is a timer. We'll get into these later on when we get into timers. Pressure switches, flow switches. We have symbols, guys. We have pressure switches, flow switches. We have temperature switches, and each one of them would have their own symbol. These would be the symbols that you would use if you hook these things up to the PLC. Inside ladder logic, we have very few symbols. Are we okay? Yes, no?
Yes.
Okay, guys, y'all take another 10-minute break. And, okay, we got. Talking about the amount of voltage that we have available. Volts we use as the units. So 12 volts. If you go out and buy a battery, it's got like a C cell, it's got, 1.5 volts. Then we have amperage, which just about everybody calls amps. So now you go out and buy a vacuum cleaner, it's going to be rated in amps. So you think the more amps it has, the better it is. It's just that it might pull a lot of amps and it's not efficient, right? You understand? So it's a measure of the amount of current that is flowing. 1 ampere equals to approximately 6.25 times 10 to the 18, which is a bigger number. Electrons moving past a point in a circuit in 1 second. In math formulas, we use the letter I. Then we have 2 types of opposition. We have resistance and we have reactance. In DC and intro, all you're going to deal with is resistance. Once you get into AC, you're going to deal with reactance. AC and DC is not the same. So AC, and DC, if you've got a 100 ohm resistor, 100 ohms of opposition, and when y'all take the class, y'all understand what that means.
Okay.
It will be 100 ohms, whether it's in AC or DC. The difference between AC, and we're going to look at this slide, we'll talk about that. Very, very important to understand. But in AC, reactance varies with what we call frequency. So a resistor will have 100 ohms. A capacitor might have 100 ohms at this frequency. It might have 10 ohms at another frequency. So these guys are really weird. We're not going to deal with that this semester. I might even take it out. Shorts and opens, this is very important. What's nice about the PLC, if you have a short or you have an open, it's going to come up there and give you an error for that run until you figure out what's going on, right? You understand? But if you wire on the output of the PLC, if you short something out, you can literally screw your PLC up. And opens, of course, we know opens don't work. So a short is an undesirable path for current flow. What you've done is you've lost control of the current. So all these control devices that we have in there are no longer controlling the current flow. So that would be like you go over to your light switch and you flip it and the lights don't turn off. It's because you have a short. And this is probably one of the most used terms. Now what happens is when people have problems with a circuit, they say, I have a short in it. Shorts blow fuses, shorts burn stuff up. Opens is what they actually have most problems with. But my mom used the term shortage. I have a shortage in it. I've got a shortage in this thing. I wouldn't say anything to my mom. So I knew what she thought. Short circuits occurs when the source conductor and the return conductor come in contact with each other, which bypasses the opposition of load, and this is not good. Short circuits are bad. These is what your overcurrent protection devices protect against. Short circuits. Short circuits cause fires. Short circuits burn stuff up. Sources of surge. So splicing, by the way, so we got conductors. So conductors do one thing in life. They do exactly what your blood vessels do. What does your blood vessels do? It carries the blood between your heart and your muscles. That's what it does. Your muscles is the load, right? All that nourishment is going out to your muscles. That's all conductors do. Conductors carries this current through the voltage source. The voltage source don't make current, by the way. All it does is create a difference of potential. That would be like saying wind makes wind, right? You understand? Your heart does not make blood. What does your heart do? It moves the blood that's there. So what it is this voltage source is creating a difference of potential, and to cause things to move, we've got to have a difference in pressures, right? You understand? Which causes all these electrons that's already in there, it causes them to move. Moves through the voltage source and the rest of the conductor. All the electrons are already there. So splicing is so eventually a conductor, we can't have conductors that are infinite lengths. And then when when Alabama Power has a line that breaks, they don't go out there and run a new line, they splice them together. So splicing is the act of taking two conductors and joining two conductors together. Eventually every conductor comes to an end. The act of bringing that thing to an end, we refer to that as termination. Technically, it's called termination. So if you ever hooked up a circuit breaker, you bring that wire, you stick it in, you screw it in. What you did is you just terminated that conductor. So incorrect splicing causes shorts. The incorrect termination causes shorts. Of course, most of the time, if something's been working and all of a sudden you got a breaker that starts popping, don't go out, guys. If you got a 15 amp breaker, don't go out and buy a 20 amp breaker and stick it in there just because it fits. Because those conductors are rated at, they're rated a lot higher than that. But technically, running inside the walls, inside all this other kind of stuff, it causes the ampacity to go down, the current carrying capabilities. So I think if you looked at the ampacity of a 14 gauge wire, which is what we use for a 15 amp circuit, it's rated like 30 amps. But that's in free air. So there's three things that can determines the opposition a conductor has. It has very little opposition. Anybody know the three things? That would be the opposition would be what determines the three things of a conductor that determines its opposition. There's nothing out there that has zero opposition at all, even the superconductor. But conductors are rated in ohms. That's our opposition rating of ohms. This rating in 1,000 feet. So if we looked at a 14 gauge wire, it might be 2 ohms per 1,000 feet, but it's still ohms. And if I push current through ohms, we get heat. Okay. There's three things that determines how much resistance opposition a wire has. It's first of all, it's how big it is. We call it the gauge. So 14 gauge, and gauges are weird, by the way. Gauges, the smaller the gauge number, the bigger the wire. So a 12 gauge wire would actually be bigger than a 14 gauge wire. So it's weird. And it's a math formula that I could show you. It's real weird how they calculate that. So it's kind of weird with people. Then it determines the length. So they're rated in how much opposition they have per length. And the next thing that determines how much opposition a conductor would have would be its temperature. When metals heat up, their resistance goes up.
How big it is.
We call it the gauge, or the size would be better, the size of it. The next is what it's made out of. Anybody know the best conductor of electricity? Silver.
Silver. And then copper, aluminum.
Then followed by copper, then followed by aluminum, followed by gold. Most people say gold because it's very expensive. Yeah. So gold, we use gold as the plating. The advantage of gold is that it doesn't oxidize. So anything that's going to expose to an atmosphere that we don't want, and copper oxide, copper rust is highly resistive. It's highly resistive. Silver rust is conductive. It's just as conductive as silver is. But it's still very expensive, right? You understand? Copper is an extremely good conductor. Well, if switches are silver plated, so usually when you look at the contacts on a relay, it'll be a dull gray, and that's because it's silver plated. Plated, not silver. It's copper with silver plating on it. It's like when you buy these coins, it says, this is a reproduction of so, it's got 5 milligrams of gold plating on it. So that means it's so thin, if you wiped it with your finger, first time you cleaned it with a metal cleaner, the copper will wipe it. So we use a lot of copper and we use a lot of aluminum. Aluminum is the fourth best conductor. In fact, aluminum is almost a semiconductor. But it's so cheap and it's so light, and we'll talk about how we can get by with that in a second. So this is why, even though if I was to look at the ampacity of a 14 gauge wire, it would say it was 30 amps, but it would say at 25 degrees centigrade. As soon as I put an insulator around there, it's like you putting on a jacket. What do you put on a jacket for? A coat on? Keep the warmth in. So now all the heat being generated by the conductor stays into the conductor, and the resistance goes up. And then, of course, now you run these things in your house. You run them through the walls and all kind of stuff, right? On the other side of your insulation, run through the roof. So this is why the National Electrical Code rates the 14 gauge wire at 15 amps. And you're supposed to fuse them or put a 15 amp circuit breaker on. A 20 gauge wire, good gracious, I don't know what that thing's, I mean, 12 gauge wire, but NEC rates it at 20 amps because that takes in all your considerations, right? Whether that thing is installed in Alabama, you know, where it got up to 100 degrees this weekend, right? Or if it's installed up in Maine, right? You understand that? It's saying, okay, it should be able to handle this 15 amps at this temperature.
20 gauge is regular.
12 gauge is rated at 20. NEC rates it at 20 amps. And you're supposed to have for 20 amp circuit. I don't know if you got a 20 amp circuit. A 20 amp receptacle is actually different than a 15 amp receptacle. So a 20 amp receptacle, I can probably do this with my. So a 15 amp receptacle, you'll have one short plug and you'll have one long one, right? The long one is for the neutral, and this one is for what electricians call the hot. So this would be like L1 and L2. If you actually look at a 20 amp, is it the short one that's got the L in, or the long one? I think it's the long one. So it's got a little slot right here, and then it's got another short one. So what happens is you can plug a 15 amp plug, you can plug a 15 amp device into a NEMA 520, by the way. But an actually 20 amp device would have that little crook in it right there. So that way you can plug something that needs 20 amp into one of these, but you could plug one. So this guy, if he can run 20 amps, he can run more. They can run a 15 amp one. So this is, they call it National Electrical Manufacturers Association. They do a lot of mechanics. They call this a NEMA 5 because that was and this would be called a NEMA 515. And then a NEMA 515P, that would be the plug. NEMA 515R would be the receptacle for that. They call this a NEMA 520. And that's why you go in. So you don't want to put one of these plugs on 14 gauge wire. This needs to be on a 12 gauge wire. 12 gauge wire. And
You can't put the 15 amp.
Yeah, you can put the 15 amp on a 20 amp circuit.
So 12 gauge is 20 amps.
Yeah, it's rated NEMA for National Electrical Manufacturer. That's what they rate the wires, because what are they compensating for? They're compensating for a length of like 100 feet or something like that.
Okay.
And then there's a math formula you're supposed to do if you go past 100 feet, and then plus running through the wall, also with that outside jacket on there, and also all the insulation. Yeah, I know. It's that I asked Hoyt about that. So if you go past a certain length, you got to add. So you might have to run a 20 amp wire for if you go so far. So we don't need to. So we're talking about stuff that's nice. This is nice to know stuff, guys. So this is technically, according to our laws, we have two laws. We have one law we call Ohm's law, which is a very important formula that we're not going to use in this class, but you will be using it in intro. And the main formula is V is equal to, if I can do this, is equal to I times R. So we use this to calculate, and it's just like anything else. What you have over distance, you have what we call a voltage drop. So you have the voltage of your source, right? You'll understand this. And then as you push it through, it's just like I've got a hose pipe out there, and I'm automatically put a restriction in it, right? So we're trying to put maximum flow, but automatically put a restriction in it. Wasn't due to the current, to the water flow. It actually goes down. That would be an opposition. Now every conductor has an opposition. It's just that it's going to be very, very, very small. I've got a chart somewhere that shows you the actual ohms per 1,000 feet. But what the National Electrical Code has to consider is these guys in the house, first of all, they're going to be insulated, number one, right? You understand? Why do we insulate wires? To keep them from coming together right? And it also allows me to handle them, right? You understand that? So that's why we insulate wires. So we insulate. Well, as soon as I put an insulator on there, well, what happens to the temperature of the wire when we put that current through there? Yeah, the temperature, but the resistance goes up automatically because they get hotter, right? You understand? No, no, we're gonna have an insulator around it. Well, it all depends. If they get these things up above where I can't get into them, so Alabama Power up on those posts, they don't insulate their wires. They use air as an insulator. So now all of a sudden, that the ampacity, those guys can handle more current because they're not what? They're not insulated, right? You understand? But where are those lines at? Yeah. Well, they get into my house where I'm going to have to handle this thing. Then, of course, we're going to have to insulate the wire. So all our wires that we're going to be using, this semester, it's going to be insulated. So this is insulated right here. You don't see the wire. It's going to be a plastic. Normally it's usually different variations. The problem they found out with plastic and rubbers is over time they actually dry rot. So now they use thermoplastics, they have different ratings. And what you'll find out is that NEC rates the wire according to the insulation. So if you've got an insulation that has the ability to run at a higher temperature, ambient temperature, than ours are, they're going to have to direct the conduction of the wire. So if you look at the NEC table for conductors, up at the top it tells you what type of insulators that conductor would have and be able to run 15 amps, and then you go to another one and that current might be yeah. So it depends on how much temperature that the jacket is the insulator designed to run into. And then sometimes we'll take multiple jacket. We got multiple conductors, and then we put them inside what we call a jacket. Those are what we call cables. So a cable is two or more conductors that shares a common jacket. Now the jackets are rated the jackets are rated for the environment. So they'll be rated for like dirt, underground, wet environments and stuff like that. And your insulators are also going to be rated in what type of environment they might get in. So these are good questions, guys. So what happens if we use this formula and we transpose it? Then I would be equal, so I would be equal to what? V divided by R. So what happens on a short circuit is your R goes to almost zero. So what happens is your current, so what's any number divided by zero? No. You got your calculator? Put it in your calculator. So people don't understand what, it's an infinite number. Right? Because what was so funny, when microprocessors first came out, they could not divide, they could not multiply. All they could do was add and subtract. So we had to write programs to make it divide. We had to write programs. So you learn right off the bat, division is nothing but repetitive subtraction. So what you do is if you're going to divide 25 by 5, basically you subtract 5 from it, and you keep subtracting 5 until it generates a borrow. And as soon as it generates a borrow, you say, okay, that means that's the answer, right? You understand? And then we figured out fractions. So how many times can you subtract 0 from a number without generating a borrow? Infinite. So yeah, so any number divided by 0 is an infinite number. So technically, if nothing had resistance and if the wires didn't have resistance, what would happen if I have a short circuit, current would try to go to infinity. Can't do that. Why? Because the wires have resistance. And also your voltage source has resistance. So what happens, your voltage source starts dropping a bunch of voltage, your wire starts dropping a bunch of voltage, creates a bunch of heat, its resistance goes up. That allows the power source to drop less voltage, its voltage goes up, and the heat goes up, and eventually it's just going to cascade on you, and something's going to happen. Either it's going to start a fire, two things are going to give up if you don't protect it. The voltage source is going to give up. So if you've got a little old C battery and you take a wire and put it across it, the battery's going to give up, right? You understand? Because it's got such high internal resistance. You go out and get a dang car battery and you put a wire across that, the wires are going to give up first, right? You understand? So either the wires are going to give up or the voltage source is going to give up. When wires give up, that's drastic. It'll burn that insulation off there in a heartbeat. A lot of your insulations that you have in houses, it'll actually carbonize. And then it'll do what? It'll just flake off. Yeah. And then the short gets even worse and worse. So what do we do to protect against short circuits? We use circuit breakers or fuses. No, circuit breakers trip, fuses blow.
Okay.
Fuses you have to replace, circuit breakers you don't, unless they go bad. By the way, circuit breakers are no supposed to, they're a control device. Circuit breakers don't get hot. If you got a circuit breaker in your house that's getting hot, it means you need to do what? You need to turn the power off, but you need to replace it. If you got an outlet in your house that's getting hot, you need to replace that outlet. If you got a switch in your house that's getting hot, you need to replace that switch. If you got a circuit breaker that keeps blowing, don't go out there and buy a higher rated circuit breaker. Figure out what's going on, right? You understand? Of course, the current will never go to infinity. It will, the load is bypassed. The current flow of the circuit will be limited only by the resistance of the conductor and the internal resistance of the voltage source. If not protected by an overcurrent protection device, somebody's going to give up. It's either going to be what? It's either going to be the voltage source or the wires. Little batteries. Anybody ever put a 9-volt battery in their pocket against change and it gets real hot under there? And it gets hot because it's dropping a lot of voltage. So then we call this a short. We call it a short circuit. When voltage flows through resistance, its resistance goes up, and resistance goes up, it creates more heat. When it creates more heat, it drops more voltage. Your voltage source will drop less, and it just keeps going. And it just cascades after that. So inside our PLC, if you have a short, it's not going to do anything because it's a program. What it's going to do is going to display the rung has an error, and you're going to have to fix it. But when you wire on the outside of that PLC, you'll understand, and you have a short circuit, you could damage your PLC. OCPDs, these are overcurrent protection devices. And we know two types. What are the two types? Main advantages of fuses are what? Cheap. The airplanes that we had, that I worked on, they couldn't have glass fuses. They had to have ceramic fuses. A lot of your high voltage fuses have ceramics inside of them. Has sand inside of them. And what that does, when it blows, it melts the sand, creates a glass in there. Glass has extremely high resistance. All the fuses on our airplanes that I worked on were ceramic. And then they had these little pop-outs up here, which is really cool. So to tell if the fuse was blown, the little thing would pop out on the side. It was spring-loaded. Can y'all see what I'm talking about?
Yeah.
And we usually check a fuse with an ohm meter. How many ohms should a fuse have? How much opposition should a fuse have? Pretty close to 0. It's got some, guys, because it's got to have R to melt, right? You understand that? And the smaller the fuse, the smaller the amperage rating of the fuse, the more resistance it'll have. Your big fuses, though, odds are, if you measure them with a ohm meter, it measures them pretty close to 0. If you hadn't had any intro yet, that's one of the things you're going to be using. You're going to be using an ohm meter. So this is normally how we check a fuse, and you need to check it. We had a guy lost his job. He worked on one of these ticker tape things when I worked for a computer company, and it didn't work. And he went in there and pulled the fuses out and checked them and put them back in. So they called a guy from Chicago, and they was paying him like $100 an hour plus road and board and plus the trip down there. He came down there and started checking the fuses with his ohm meter, found a blown fuse, put it back in there. And the guy lost his job because he didn't check it. Yeah, and that was the problem with these glass fuses is people will look at them. But what had happened, it had blown inside the cap, that little metal cap on the end. Normally they don't blow that way, but they do. And these are circuit breakers. Everybody's used to these guys. So what would be the biggest advantage of a circuit breaker?
Reset.
Yeah, we have to reset them. Normally a fuse will pop, we can have fast blow fuses, so another big advantage of a fuse, usually it'll blow faster, and this is one reason a lot of industry still uses a lot of fuse. The main reason is that they're a lot cheaper, but sometimes they're just a lot faster acting. So this would be an example of a short. So this is a series parallel circuit. We don't have these, but this would be a short. So what would happen is this guy right here, this guy here would make up the difference. So a lot of times when you have a short, it will cause the other load in a series circuit to go bad. So you probably notice a lot of people when they blow one of their little old bulbs, they'll take a piece of aluminum foil and jam it in there. If you ever notice, all the other lights are a little brighter, and if you hit them, they'll pop real easy. Yeah. So this would be a short. This would be a short. This would be a short. This would be a short circuit. This is what's bad when that source conductor, when the two main conductors. So now the only opposition you have in the circuit is the wires and the internal resistance. This is what gets us in trouble. Insulators, of course, we know what insulators are for now. They help prevent short circuits and also allows us to do what? It allows us to handle conductors. Insulators, by the way, are rated in how much voltage they can keep in. So conductors are rated in amps. Insulators are rated in volts. Because that's what's keeping that pushing. It's just like pipes. You got a Schedule 40 pipe, right, or Schedule 80 pipe. I don't remember which one has a thicker wall, but one of them has a thicker wall, which means it can keep more water pressure in, right? So that's what insulators are rated. Jackets are rated in environment. So sometimes your insulator and your jacket are the same. A lot in cables, though, your insulators would be different. If you ever played around with a house wire, you can actually see the jacket off the conductor. If you strip it, it's got a little clear coating on the actual conductor. So they have both of them. Opens allows no current to flow through the load. On-off switches, we do this deliberately so we deliberately create opens. But then open circuits are created by fuses and circuit breakers, broken conductors, faulty splices, faulty termination, or excess currents causing the conductor to do what? Melt. They will melt. Oh, I need to check out Big Bertha over there. We usually burn up a wire with that guy over there. See him in the corner. So this would be an open. 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 This would be an open circuit. Yeah, no flow.
What could cause that to happen?
Well, one, a light switch or a push button. So we create open circuits on purpose. On-off switches, fuses, or circuit breakers, broken conductors, faulty splices, also defective loads. I should put that in there also. Excessive current causing the conductors. Any more? We had the planes that I worked on in the Navy, they're nothing now. These they're P-3 Orions. These planes cost like $32 million. And we were upgrading. We were one of the squadrons to upgrade from a P-3B up to a P-3C. And we got these brand new planes in, brand new. And we had problems with one of the generator control panels. The generator would pop out, and we went out there, and the guy had stripped the wire. He didn't strip it all the way, and when he put it into the conductor, he put it down on the dang on the actual insulator. So what was happening is this little end would touch every once in a while. When the frame would vibrate, it wouldn't work anymore. $32 million airplane. They just decommissioned the P-3. The Navy is not flying the P-3s anymore. And the squadron that I was in, VP-40, they flew the last combat mission, the last mission, last deployment with the P-3s.
So you still work with the airplane?
No,
Oh, no.
I teach. I don't do any outside work anymore.
Okay.
I don't need to. I used to do a lot of outside work, but I don't do that anymore. So this is the difference. So direct current flows in what?
One direction.
One direction.
Flows from the negative terminal to the positive terminal. By the way, some people teach us what we call conventional current. Originally, when they knew something was flowing, but they didn't know what. And they came up with the two polarities, positive and negative. That's what they came up with. And originally, they thought that the current flowed from positive to negative. Then after a while, when they got into a lot of physics, they understand that it was the electrons that was actually moving. So electrons moves from negative to positive, right? So we have a negative potential that pushes the electrons out, and the positive potential is pulling them back. Some universities still teach what they call conventional current flow. Conditional current flow is current flow positive and negative. Now, what you find out, guys, it don't change any math. Everything's the same. The only thing changes is the rules of magnetics, electromagnets. So when you put current through a wire, they have what they call, I keep them confused. One of them's called the right-hand rule for 1, and for conventional current, you just say the left-hand rule to determine which would be the North Pole and South Pole. This is one big advantage of DC. First of all, we can create it magnetically with DC generators. We can create it chemically with batteries. We can treat it with thermocouples with heat. We have solar cells, which a lot of people use, which is created DC with light. We can use piezo, which means force electric. These are these cigarette lighters a lot of people have, where you shock a piezoelectric crystal and it generates enough voltage to create that spark. We can create it electronically, thank goodness. We can have AC to DC converters. So that's what this guy is right here. This thing on my computer. This computer don't work off AC. It works off DC. This is the AC to DC. Over here, this is AC. Over here is DC. So that little cube that you can find, little brick, that's a AC to DC converter. We call them power supplies. Major advantage of this, of course, is that we can control it electronically. So electronic devices operate off of DC. Even if you plug them into the wall, they operate off DC. They have a converter in there that converts what? AC to DC that we call power supplies. And plus, another big advantage of DC is we can store it. So we store it. So we can go from DC to AC too, by the way. That's correct. So, and you can figure it. So direct current is current flow in one direction. So what would our alternating current be? Two directions, back and forth, alternating. So this is the big advantage of DC right here. We can do what? First of all, electronic. So your car has an alternator on it. What does your car run off? It runs off DC. So you got a converter in there that automatically runs off. They call them rectifiers. It takes what? The DC, AC, and converts it over to DC. But even with DC, I can reconvert DC. I can take DC and convert it into AC. Electronically, because once I've got it in DC, I can electronically. Thank goodness, we wouldn't have stereos because your speakers run off AC, but your power your radio off what? DC. So your radio is a what? A DC to AC converter. So because we can electronically control it, which is pretty neat. Pretty cool. So these are batteries. Bioelectric, by the way. Did I have bioelectric in there? Yeah, bioelectric. So this is not going to be on the blackboard, by the way. I just found this one. DC batteries, DC generators, AC DC converters are what we call power supplies, solar cells, piezoelectric, thermocouples, and then I'm a bioelectric. I create electricity. And that's what your brain processes, right? Electricity. And anybody that watched the metrics, y'all understand that, right? So in the metrics, they use this as what? They use this as batteries, right, to power their, put us in a dream world. So we might be in a dream world right now, right? AC, alternating current, constantly swaps directions. The voltage source in an AC circuit constantly swaps polarities, which causes the current to constantly change direction. One thing that's a lot easier to generate. It's extremely efficient to transmit, and we'll talk about that in a minute. Voltage levels can easily be changed with transformers, not transformers that change shapes, electrical transformers. We had a guy in the day class brought that up. I said, what's a transformer? AC motors are less expensive per horsepower. These are produced by AC generators, electronically, very few in bioelectrics. The only thing, but I didn't know this until I started researching this a long time ago. But we can't store AC. We cannot store AC, right? You understand? So there's no such thing as a rechargeable AC device. We could take it and convert it to DC, charge a battery, and then convert it back. It's like these big old windmills and stuff like that. Those suckers put out DC. And then they store it, right? You understand? And then they convert it to AC. Solar cells, which is the big thing now. So this is what I didn't know. This is what I didn't know. Electric Eel actually puts out 65 10 volts AC at 25 hertz, which you'll look at in a minute. He uses this to stun things, and it uses 870 volts, approximately 870 volts to kill things. Then we have automobiles use this thing called an alternator. It's actually an AC generator. And some people have these AC generators. I have one of them ever since the snowstorm of '93.
Yeah.
So I got my house wired so I can switch over between my generators. Then the power plants, big old power plants, electric eels, DC to AC converters. You can have. My wife's got one in her van, so she's got a regular NEMA 20 plug in there. So we can just plug regular devices in. It's on the wall in there. So it's got an AC to DC to AC converter. And then these things called function generators, which you'll run into when you're here. I think we might have one up here. No, I don't see one. So why do we need what we have is where's the power company here? Alabama Power. We don't. This Bessemer, by the way, is not on Alabama Power. Y'all know that, right? We're on TVA. So where's our generators at? I don't think that's TVA. It's TVA. They're up around the Tennessee River. They're up in way up in North Alabama. So they got to get all that power down here, right? You understand? And you don't pay a voltage bill. You don't pay a current bill. You pay a power bill. And the main formula to calculate the power, and you'll learn this. I don't think y'all do. Do y'all do power in intro? You should. Yes, it's a force. Yeah, so it's actually pressure times speed, but that's okay. So power in electronics, if I can get this to work, guys. I really need. We call this Watt's law. I didn't think y'all did power in intro. I think power in DC. Yeah, I think y'all pick up power in DC. I think. I don't teach those classes anymore. So P, the amount of power we get in watts is equal to I times V, or backwards, or E times I. And then what we learn in formulas real fast, instead of transposing this, if we got a multiplication formula, I can put what's over here on this side, and then I can come over here and put the other two items right here. And then what you can do is you just cover up. So you come up here, if you cover up the P, it would say, these are side to side, it would say P is equal to V times I. If you wanted to solve for I would be equal to P over V, right? You understand that? And V would equal to V over I. Current. So I is the current. And then V is volts. And then P is power in watts. So the actual answer would be. So this is what you pay for. Okay. Everybody okay? So the problem we have is Alabama Power, or TVA, is trying to get that power all the way, and you don't pay a voltage bill. You don't pay for V, you don't pay for I, you pay for watts. Okay. So, and then we have what we call Ohm's law, which is V is equal to I times R. So then I can transpose that. I put V at the top, and you will run into this in intro. So this says, if I wanted to solve for the amount of I in the current in here, if I knew how much voltage was in the here and how much opposition, then we could solve for the amount of current. Right, everybody okay? And of course, if I knew the amount of voltage and current, then I could solve for the amount of resistance of the circuit. And then of course, the first one up there. So technically, when I turn on, if everything was 100% efficient, I turn on a 100-watt light bulb in my house, how much power would my power company give me? If I turn on a 100-watt light bulb in my house, how much would the power company give me? Works, guys. 100 watts, right? So basically, they're trying to deliver watts. They're not trying to deliver power. They're trying to deliver watts, right? You understand? So this is the big guy that Alabama Power looks at. Alabama Power looks at this guy right here. It looks like I is equal to P over V. Now the problem is if I put current through resistance, it's going to drop a voltage, right? You understand that? And every wire has resistance. So Alabama Power, your power company, calls it line loss. This is how much push you lose over the length of the wire. Well, look at this formula right here. I, which determines, I can't do much. Well, the only thing that determines the resistance of the wire is what three things? The gauge, the size, the length, and the temperature. Okay, you understand that, right? So that's not true. More than that, we left off one, which is very important. The gauge, the material, excuse me. Yeah, we left that out, guys. That's a big thing. Let's start off. It's the material. Let's start off that first.
Okay.
Then it would be what? The size, length, and temperature. Okay, guys, I'm sorry I left that off. I'm going to go back and edit my recording. So when I put current through R, it creates a voltage. But look at this guy right here. I is equal to P over V. And I'm trying to give you what? I'm trying to give you watts. So that means if I come over here and I want to send you 1,000 watts, and I do that at 10 volts, how much current would that be? It's going to be 100 amps, right? Okay. Let's say I come over and I'm trying to send you that I, but now I'm on a sign to send it at 1,000 volts. Then what would my current be right now? Be 1 amp. Okay, so if Alabama Power can step their voltage up to 750,000 volts, which TVA does, they could send 750,000 watts of power with 1 amp. So this is what a transformer does. A transformer allows them to step these voltages up. Now we say transformers change voltage, but transformers also change the amount of current that's required to deliver that power. So as I step the voltage up, the current is going to do what? It's going to go down to deliver that power. So they step it up real high for transmission. And then they start stepping it down when they start getting close to me. So the advantage of high voltage is that we can create those watts with less current. The advantage of low voltage is that it's safe. So this is why you got 200, you got two voltages at your house. What's the two voltages? 240 and 120 is what NEC's. What's all your high wattage loads running off of? 240 at your house. Yeah, 240, right? Why? Because they can run smaller gauge wire. People would say it's more efficient. It's not more efficient. It's cheaper to install. It's cheaper to maintain. The higher the voltage, the smaller the wires. The smaller the contacts on the relay has to be. The relays don't have to be, right? Y'all understand that? So it's cheaper to install. It don't cost you because you don't pay for voltage, you don't pay for current, you pay for watts. Now the problem is your loads are designed, these loads are designed around certain voltages. You can't take a device running off 240 and run it on 120. It wouldn't work. It'd be 1/4 of the power. We're not going to explain that. So power varies with the square of the voltage. So a lot of people think if you double the voltage to a circuit, power goes up by 2, but it only goes up by 4. If you half the voltage to a circuit, it drops down by 1/4. So Most people don't understand that. They'll think it varies proportional, but it's not. So this is this is the advantage of AC. The problem, what's nice about DC don't work in a transformer. So DC, to induce a voltage, to induce a voltage magnetically, guys, I need to pause my lecture. Maybe it'll pick me up. I don't have a camera up here. So this is the way Alabama Power works. So this is a little lamp meter right here. And then I have a bunch of wires. And I have a magnet. Excuse me. So I'm going to go over and put that magnet up there and nothing happens. You know? I'm going to come over and start doing this. What am I making? I'm making current. At a voltage. I come over here and all generators spin, right? If I come over and spin my generator, you can see what's happening. So one way, if I get close enough, one way it deflects one way, the other way it deflects the other. So this would be AC. Okay. So to produce a voltage or current into this wire, I gotta have three things. I gotta have a magnetic field, right? You understand that? I gotta have conductors, and then I gotta have motion between, we call it relative motion. So either if I could pick that magnet up, I could leave the coil stationary and move the magnet, right? You understand? Or the way I'm having to do it, since the magnet is so heavy, I'm spinning this. So what's nice about AC's got all that, right? You understand? Mm-hmm. So transformers, if you ever look at them, it's just a bunch of coils wire. And then AC creates motion. It automatically does what? The magnetic field would fan out, right? You understand? And then it would collapse back in and swap direction. So right off the bat, AC has motion. DC has no motion. So DC and transformers don't work off DC. Transformers work off AC. So what we can do is we can bring two coils of wire close together. We can couple them with a piece of metal, and we have what we call a secondary and a primary. And we can induce voltage across that coil right there. And what determines is the number. So what determines the amount, of course, will be the strength of the magnetic field, the number of loops you put in your conductor, and of course the speed of the motion. Yeah. That's the three things that determines the amount. That's exactly right. So what we're saying is that I can change the ratio. So if my primary has 5, for every 5 turns over here, I have 1 turn over here, the transformer would divide by 5. If I have 5 turns over here and I have 100 turns on my secondary, the transformer will multiply by 20. So we have what we call step-up transformers and step-down transformers. So we step it up for what? Transmission, and then we start stepping it down with these transformers until we get down to your house. Then we have 2 voltages. Over in Europe, they only have 1. They have 240 over there. They electrocute a lot of people, right?
Why would they do that? I mean, like.
It's just the way the power grid's set up. We have two countries.
Right.
So we generate AC at 60 watts per second. Actually 120 watts per second. And we'll look at that in a minute. They decided to use a 50 cycle grid over there. So there's all this, and their plugs, they don't use NEMA plugs over there. They have their own plugs over there. So if you ever go over to Europe, guys, you're going to have to buy these little adapters. And if you have something that runs off 120, you got to buy these little transformers, a transformer for you. Most of your little bricks, so these are special DC to DC converters we call switching power supplies, and they'll work over a range. So if you ever looked at your little brick, it usually says 120 through 240. So you can use those over there. You just got to buy that adapter. So they have round plugs over here. We have straight plugs.
Oh, the circle.
Yeah, they have circles. You'd have to look and make sure you got the right adapter. So I've got an adapter that you switch. It's got different plugs on it, so I could go several places. So I had an opportunity to go over to Berlin, Germany for 2 weeks. I went a lot of places when I was in the service, but we didn't have cell phones when I was in the service.
Right.
So this is the way AC is generated. It's generated on a circle, and it's called a sine wave, guys. Whether you understand it or not, we can calculate the instantaneous voltage by using a little tree. So this is called a sine wave, and this is the way AC is generated. Pretty neat, huh? So we called it, we rate it in degrees. So we say one cycle would be equal to 360 degrees. So 360 degrees of one, it's just like 12 midnight. What's 12 midnight? It's the ending of one day and the starting of the next. So actually, 360 degrees for one cycle would be 0 degrees for the next one. This runs off and on and on and on and on and on and on forever until you turn things off. At the output of a transformer. No, you wouldn't see the circle. It's just that it's generated on a circle. That's why, even if we do it electronically, we call this a sine wave because the voltage that we get out, the voltage, current, and power we get out varies with the angles, this angle right here. Yeah, so right there we hit peak. So we hit peak, we have two peaks. We have a positive peak and we have a negative peak. And then it goes to 0 twice per cycle. We call it a cycle. So Alabama Power is generating 60 of these every second. So 60 cycles per second. Well, yeah, these guys right here, you're right. So these guys right here, what's the difference between fluorescent bulbs and incandescent bulbs? And you can tell it a lot of times when you take a picture under fluorescent bulbs, it appears yellow. These guys are actually turning off and on 120 times a second. Completely off, 120 times a second. But to us, they look like they're on all the time. And this is why a lot of times you'll have a shirt that looks different inside fluorescent lights, and you go outside and it's a different shade because of the number of wavelengths. So this is some terms we probably need to know. So one repetition is called a what?
A cycle.
Cycle. And by the way, we don't get this work out of here. We don't get, so if this right here is 170 volts, I don't get 170 volts of work out of this thing. Because it only hits one, just think about it, 60 cycles per second. That's 16.666 milliseconds, 0.016 seconds for a complete cycle. Each one of these alternations is going to occur every 8.33 milliseconds. 0.0083 seconds. So how long is it sitting at that peak voltage up there? We just couldn't comprehend. It's just there in no time at all, right? So it hits that peak voltage for a heartbeat, and then it's down, less than a heartbeat. And then it's starting down. Then it hits 0. How much work are we getting here?
None.
None. So what happens is we get what we call, it's not an average. We can't call it an average. It's called an effective voltage. Because if I average this out, for every positive, we would have a negative. And that's a big problem we have. Let's see if I can do this. I'm going to put this on AC, turn this guy on, put it on volts, 200 volts, and I have it on AC. So this is a meter that measures both resistance and it also measures we got it set to measure volts. I'll put it in the outlet, being careful up here. And, oh, I'm not in there, sorry. And what does it say we have here? Okay, now what I'm going to do is I'm going to come over here and tell it to give me the DC average. So I'm going to put the meter on DC. What do you think it's going to say? Zero. Because this is an average. So what's happening is DC-wise, your positive alternation is counting your negative alternation or positive alternations, or the average would be 0, which means, okay, I don't get any work out of these things. Average DC is 0. So they had to come up with a method where they could come up with something besides an average. And so we called it effective voltage. And let's see if that's in here. So this is some terms. Cycle, alternation. Everybody okay on that? Frequency is the what? Is the rate. And anything that's repetitive like this, computers runs off a pulse, a digital waveform. but it's going to be repetitive, and that's some of the things they rate microprocessors in is speed, right? There'll be gigahertz and stuff like that. And the period is the time it takes for one cycle. And that's where so 60 cycles per second. So I would take 1, I divide it by 60, and it comes up and gives you 8.66666 or 0.083, 0.083, 0.0083 seconds. Right? Y'all gonna have to learn engineer notation, guys. Have y'all got there yet? Yeah, you're gonna get there. The intro, you're taking intro this time? Oh, okay. EET 100? Okay. So we use a lot of engineer notation because it just sounds cool. If I can get this thing to draw. Engineer notation is a form of scientific notation, but what we do is we always move in groups of 3s. So what we would do is if we have a fraction that looks like this, then we would take that decimal point and we would move it in 3s. So we're going to always move in 3s. So I'd go 1, 2, 3, and then I would stick 2 more zeros out there, and I'd go 1, 2, 3. And then we have different things. So if I move it over 3 spots, we say that's 10 to the minus third. We call it milli. If we move it over 6 spots, 10 to the minus 6, we call that micro. And we use the Greek symbol for micro. If we move it over 12 spots, what's 12? Well, if we move it over 9 spots, what's that, guys? Nano. If we move it over 12 spots, I'm waiting. Pico, good. We're not going to deal with that a lot, but so we'll say, so if I've got 0.0086 and it keeps going on forever, and we're going to drop it sooner or later, then I would come over here and move that 1, 2, 3. And what I'm doing is I'm looking for whole numbers, but I always move in groups of 3s. Well, I moved it over 3 spots, so I would say 8.67 milliseconds or milli, whatever it was, right? That makes sense now. So we use that engineer notation, and that's the name of the game. So if you got out there interviewing and you said you had 0.0223 amps, a guy would say, "Oh, you just blew the interview." It's just like I tell you about the guy that interviewed for the job for it's another class. We had a guy that interviewed for the job, the teaching job, here when Mr. LaGrange left, and when he gave his presentation, he decided to give it on transformers, and he said transformers step the power up and step the power down, and he lost the job because transformers don't change power; they change voltage and current. Right? You understand? He lost the job. So, and Miss Bush came in there. I forgot what she lectured on, but she didn't lecture on transformers. So that's what they had to do when they interviewed for the job. They actually had to give a sample lecture about dealing with electronics, and we let them choose their field. This guy worked for the city of Birmingham. I'm gonna need to quote there. Some of you might know it. Yeah, with my own. But yeah, he said that transformers step power up and down. He lost the job. So when I say 8.66 milliseconds, and then I tried to rephrase it 0.0086 seconds, that's for one of these. This is 16, this is 8.3, this is 16, this would be for 60 cycles, which is what Alabama Power. So Alabama Power, we're on a 60 cycle grid, and everything's got to run 60 cycles because transformers are designed around a certain frequency. So if they took a 60 cycle transformer from over here and sent it over to Europe, it wouldn't be near as efficient because it's designed for 60 cycles. And there's a lot to do with frequency. But so this would be, one of these would be 0.0083, 33333, right? But usually we stop. This whole thing right here would be 0.0166666. It's 16 milliseconds. But that even sounds good, right? sounds technical. So, in talking the language of the trade, so you probably really need, the next class is take that intro class and they'll get you into all this engineering notation. Three-phase power. Three-phase power is more efficient to generate. What's nice about three-phase power is that we can add, so we got to have two wires. Everybody understand that? No matter whether it's AC or DC, we got to have two wires. So on three-phase, we add one more wire and we can send out 73% more power with one wire. It don't go 1/3, it goes 73%. In fact, the formula, we multiply everything by the square root of 3, which is 1.73. And if you multiply something by 1.73, it's 73%. So I can send 73% more power by adding one wire, or it will take, I could divide by 1.73, and that would be the current required to send that power. So Alabama Power uses three-phase to transmit it not because they can send more power, it takes less current in each conductor to send the power, right? Less current in each conductor means the conductor has best. By the way, what happens is we step these power companies step the voltage up so high that on their high power lines, the ones that they don't even use copper anymore, they use aluminum. And what's the advantage of aluminum? It's a lot cheaper and it's a lot lighter, right? You understand? So that means these big towers don't have to support near as much weight, right? You understand that? And it's a lot cheaper. When they start getting down to us, they start moving back to what? Copper, yeah. And it don't look like copper because it's oxidized. So just about all these regular telephone poles, this is copper wire they're running up there. Primary use for three-phase induction motors, which are very cheap, very efficient, very easy to control. Three-phase power supplies. What's nice about going from three-phase to DC is it takes a lot less filtering. From going from single-phase over to DC, we got to do a lot of other junk to them. And then three-phase drives. Well, normally we use three-phase for power. It's high power. So what happens is that single-phase will require one transformer. Three-phase requires 3. Transformers are really, really, really expensive. So if I'm going to send you a couple of 100,000 watts, I'm not going to use three-phase because the cost of adding the other transformer and running that other conductor will be too high. If I'm going to sell you 500,000 watts, then by George, I'm going to give you three-phase. So now the cost overrides overrides it. So your house is running on what we call single phase. So this is three-phase. So it's generating 3 phases, and then they're out of phase by what we call 100 electrical degrees, 120 electrical degrees. This is three-phase, but it's on 3 different wires. I wish I put a power curve up here. It's really neat. A three-phase motor will spin. A single-phase motor, we got to force a magnetic field to shift. By the way, all electromotors work on the principle of electromagnets. So this is three-phase. So this is a three-phase motor that we have right there. And, we run one back here on a PLC toward the end. I'll show y'all that thing right there. So we got a three-phase motor running off that through a relay. So. Now, normally what they do to reduce the size of the wire, they usually run them in groups of 3s.
3 wires.
Yeah, 3 wires for each phase. And this is on your high voltage lines.
Right.
Because they're still sending a lot of power. And so you'd still have conductors that would be too big to even roll in a row, right? These are all stranded wires, but they're still rolled up, right? You understand? And then another advantage of using individual conductors, if one of them breaks, then they can still send power, but at a reduced power. Y'all seen these before?
I just opened one now.
You do? Of course, we've already looked at these formulas. This is 3. So normally it depends. So these are 3-phase transformers. So these would be actually the 3 transformers were built. The 3 coils they're on top of each other, by the way. There'd be 3 sets of them. The advantage of this is it's cheaper for your initial installation, but the problem is it costs a lot more to replace. Normally, Alabama Power or your power company does a lot of this in three-phase. They'll have 3 transformers up there. They're single-phase transformers, but they're wired to do three-phase. These cost a lot more to install, but if that guy fails, you have to replace all of them, right? You understand? If one of these fails, you replace one transformer. So you'll see most of your big substations will have individual transformer banks. Your smaller smaller substations will probably have one. Our little substation over here, they got struck by lightning the other night. We have one transformer over there, but it'll be a gang transformer. And y'all seen substations before. What substations do, and they're isolated. They have bus bars across the top. They have these big transformers in there. They have a bunch of other stuff too, by the way, that we're not going to get into. They help regulate the voltages that they send out. They compensate for stuff that happens in DC that don't happen in AC. I mean, it happens in AC that don't happen in DC. And they hum, right? So this is just a little illustration. This is the kind of book that I published. So this is my drawing. So over here, I'm trying to send 1,000 watts of power, and I'm trying to do it at, I think, either 120 or 200 volts. I can't remember what it is. So it's going to require, it'll say it. So over here, it would require 8.3 amps over at my house coming out of this transformer right here. Now over here, we have how many volts? 2,300, right? You understand? So on that side, we're still dealing with single phase, by the way. Then all of a sudden, my current has dropped down to 435 milliamps, 0.435 amps, which means now I have less line loss over there, right? Then I go to a substation that steps it down. You know, everybody sees these all over the place. This would be, now we're down to, at 250,000 volts, we're down to 3.6 milliamps, or 0.0036 milliamps to get 8.3 amps over here. Is that code? So I have less line loss, which means now I can drop the gauge of my wire down, or instead of using copper, now I might go to what? Aluminum. And then we get back over here. Power companies usually generate around, here they're generating 2,300 volts. I think they usually generate around 600 volts, to tell you the truth. So normally, because the higher the voltage that's being generated, the thicker your insulators have to be.
Okay.
So we're back over here to 2,300, which is 400. Now, this is not exactly true. This is assuming that the transformers are 100% efficient. Unfortunately, there's nothing that's 100% efficient. So power in is not going to be equal to power out. Power in will always be a little higher than power out, because a transformer, if a transformer gets warm, you know it's losing stuff, right? Understand that? For our purposes, though, we're over on this thing. And most transformers out there is about between 95 and 98% efficient. So normally we assume, just for demonstrations like this, that the transformers are 100% efficient. So if I turn on a 100-watt light bulb, Alabama Power might be giving me 120 watts just to compensate for the efficiency of the power grid. So now y'all know what advantage AC has. What can we do with AC? The biggest advantage is we can step it up for what? Transmission, and then we can step it down for safety. If it wasn't for, well, originally when they first came out, Edison was the big one. Edison's DC. He loved DC. So he developed these DC generators, and I can't remember the first city they tried to, I think it might have been Chicago. And they had to have a power station every mile because DC. They couldn't step it up, they couldn't step it down, right? You understand? Yeah, just because you'd have so much line loss, right? You understand, between states. So they had to have, so they had power. How many of y'all live next to a power plant? Yeah, I think our closest one, Alabama Power, is like down in Wilsonville. And they transmit that power from there, but they step it up to get it to us, right? You understand? And then step that voltage down to the closer they get to us. And we can't store AC. So if I needed to store AC, what would I do? I'd convert it to DC, I would store it. And then I needed it back to AC, I'd electronically regenerate what? AC. Yeah, y'all can buy inverters for your car. Hook it up to your car battery, power up 120 volt item right off your battery. Because it's done, we're going DC to AC, right? You understand? Electronically. Where's your rip? This is, you need, as far as this goes, this is just nice to know stuff, right? You understand that? So what they did, they came up with a method to calculate voltages that where the negative voltage does not cancel out the positive voltage. So the method they came up with, what they refer to, so anytime I square a number, what happens to the sign? If you had -2 and you squared it, you'd come up with 4, but it would automatically, because a minus times a minus is a plus, right? You understand that? So if I square a number, it drops the sign. Then, so what they do is they take a lot of equally spaced on the negative and the positive waveform, and the first thing they do is square them. Then what they do is they take the average, which another name for the average is the mean. Then when they get through, they take the square root of it, and then that's what they come up with to be the effective voltage, and it's called RMS, root mean square. Root of the means of the squares, basically what it stands for. So if they don't tell you, so your house, when we said 120 volts, that's actually 120 volts RMS. When we say 240 volts, that's 240 volts RMS. So usually, and meters measure RMS. They don't actually measure that. What's so neat that if it's a sine wave, which means your positive alternation and your negative alternations are perfect images of each other. They will flop right on top of each other. And the voltage varies as the sine. That will always be 0.707, right? Which is the sine of 45 degrees, by the way. Your battery's running low, so I'm just going to plug my power supply. I turned it off. 0.707 is the sine of 45 degrees, which don't mean anything. But we could take the peak voltage, this peak voltage right here, right there, and multiply it by 0.707, and that would give us what we call the effective voltage. And that the effective voltage does exactly the same work as DC does into a resistive load. So 120 volts DC and 120 volts RMS would do the exact same work into a resistive load. But it only, so you have two types of meters you can buy, guys. You can buy what we call just regular meters. What regular meters does is it takes the wave and divides and multiplies it by 0.707. Then with the advent of the microprocessor, these little old processors, they can run programs. So we've got meters out there now, guys, that can calculate RMS. These are called true RMS meters. If you're working on variable speed AC drives or anything that puts out an AC sine wave that's non-sinusoidal, it's kind of, you need to have a true RMS meter. If you're just working on everything else, an RMS meter works fine. So people will go out and buy these true RMS meters, they pay twice the price for it, and they go out here and use it to work on houses. Just like people buy these iPhones, right? And then all they do is check email and text on them. They got all these features on that iPhone. They're paying all this money for, and they don't do anything. They could probably got a flip phone, right? You understand? People go out and buy cars, got all this stuff on it, right? Yeah. So true RMS, and people brag about that, like what they got on their iPhone. You know, I got 32 gigabytes worth of memory on my phone. You don't have any applications installed on it. So here we go. And we're not going to look at this. Let's not look at that. We did talk about this a little bit. We did need to talk about this. And the problem we have with the power grid is the power grid is exposed to a lot of stuff out there in the environment. So last night, We had a big lightning strike, right? You understand? Lightning strikes are billions of volts. And they're going to try to induce a voltage into everything. So we've literally had test equipment blow up. We had a bunch of computers. This was back before we had Wi-Fi. So everything was hardwired through Ethernet. And we had a firewall over an A building. And they didn't want to punch a hole. They couldn't figure out how to punch a hole through the firewall. So what they said, they had these vents on the top of the roof. What they decided to do, they were going to run this network cable out the vents, across the roof, and back through another vent, back into the classroom. We had a lightning strike, and it blew out like 50, about 20 computers down there. It blew out the network card in all of those computers because they run it up there. So the problem we have with meters, these meters, is they're sealed up really well. And the problem they was having when they had these big voltage spikes like that, these meters would literally blow up in people's hands. So what they did is they started coming up with the design of meters, and they call it categories. They have what they call Cat 1, Cat 2, Cat 3, Cat 4 meters that you can buy. It has nothing to do, what it does is it tells you how much of a voltage spike the meter can withstand, guaranteed. And you need to make sure it's either ICE or CE certified or UL certified. And what they do is they put the category of meter. So this is a Cat 2 meter. It's usually down toward the plug. So this is a category 2 meter. And what they'll do is they'll rate it at a voltage too. So I'll show you the category meters. So here we require you a Cat 3 meter, a 600 volt Cat 3 meter. So 600 volt means it will be protected up to a 600 volts, up to 600 volts. Anything above that, the spike could cause your meter to go bad or cause your meter to blow up. Okay. So we don't have near that here, and we're pretty far away. So basically it's set up like this. The further you're away from the actual service itself, this is where the category meter runs. So here we're a long way from it. We're actually running on electronic equipment. You know, we're working inside electronic equipment. So here they say, okay, you can use the Cat 1 meter. We get over here and we're working on single phase power like appliances and PLCs and stuff, PCs and stuff like that, and we should use a Cat 2 meter. We get over here on this side, it's directly next to the service coming into our place, then we need to use a Cat 3 meter. And then we get out on the distribution side, we need to get up to a Cat 4 meter, right? That makes sense? Okay, now we have transformers, we have our own substation, we have our own switch gear over here. So we want you to get a Cat 3 meter because one thing, we're working with 250 volts.
You say Cat 3?
Cat 3, 600 volt meter. Need to make sure they're CE or ICE or UL certified. This is usually on the back of the meter. So you should be able to see the back of the meter. So if you go out to Harbor Freight, you buy a meter and it says it's the Cat 3, and you look on the back, it says it's not, that Cat 3 has not been certified by anybody.
Wait, did you say Harbor Freight?
Yeah, I said Harbor Freight. I like Harbor Freight, by the way. You just don't buy certain things from
You don't
Harbor
buy
Freight.
meters there.
Huh?
That's what you told us last semester.
What's that?
You told us not to buy meters.
Not to buy a meter there. Yes, that's what I was saying. If you go out to Harbor Freight and it says Cat 3 and you turn it on the side and it's not been certified or anything, you need to be leery, right? So you know all these places, what they do is these companies, a lot of these are nonprofit, and what they do is these companies will pay to be certified. And then they'll send these things out there, and then what UL does is verify that thing does, it meets the standards that they say it does, right? You understand? So they break stuff, they tear stuff up, you know, they burn stuff up on purpose. This one is CE certified, and it's ICE certified. Yeah. So this is the difference, guys. ICE is usually over in Europe. Normally we're over in UL approval. By the way, UL changed their names. It's not Universal Laboratories anymore. I forgot what it is. So what it says is if I've got a Cat 3 meter that's rated at 600 volts, it would be able to handle a 6,000 volt spike without blowing up the main. I take that same meter, 600 volts, go to a Cat 2 meter. It's only rated at what? it can handle a spike of 4,000 volts. A Cat 1 meter could only handle a spike of 2,500 volts. So it all depends where, if you work out in the industry, normally you'll have it double rated. It might be rated at a Cat 2. It might be rated at a Cat 2 of 1,000 volts. And then the meter might be rated at a Cat 3, 600 volts. So a lot of times they'll do that. That makes sense? So that means if you used it, you could get up to a 1,000 volt scale, but it would only be protected for 6,000 volts, right? Okay. UL does not cover the Cat 4 rate of the Cat 4 category, which is this guy right here. So 600 volts, this guy is good for 8,000 volts spike. So the meter you buy for this, you don't have to buy a meter for, where do y'all buy y'all meters? Y'all buy y'all meters in DC, right? So you need to make sure you get one that's at least a Cat 3 meter, right? You understand, 600 volt Cat 3, which will do you everything here. Most applications, it'll do it for you, right? If you're planning on working in an industry, most industries will provide you their meters. That's one thing, they will provide the meters. Most of them do. And they should give you one that's. Go ahead. Somebody gonna say something?
I was just saying, most of the brands that they'll get you is the Fluke.
It's a fluke.
Fluke is, but as long as they're UL approved, guys, it doesn't really make any difference. What you got, Fluke is nice. I mean, they're the top line of meters. But as long as you get a good meter, so like there's quite a few of them out there. We have Snap-on. Now, Snap-on, I don't know who makes Snap-on. Snap-on don't make, Snap-on don't make meters, but they sell meters, right? You understand? When you do your meter certification in DC, you'll be using a Snap-on meter. And I think it's a Cat 4, Cat 3 meter, if I remember right. I can't remember what the Cat, but the Cat 3 is rated higher than the Cat 4 because the meter, there's a lot to it, and that's a really good class holder. So you get several certifications as you go through here. One of them, you'll be getting a digital multimeter certification in DC. Which basically now you have a piece of paper that says, I know how to use a meter, right?
Correct.
That's certifications are okay. You go into work and you say, do you know how to use a meter? Yeah, I know how to use a meter. But if you got that certification, they want. They know you do. So guys, what we're going to do tonight, the rest of the night, we're going to let y'all go ahead and take a break. Y'all know where the hall building is at? That's hall building. So if you hit this perimeter road right here, and you bear to the right, it's the last building on the right before you go out what we call the south gate. Y'all know the second gate down there? It's got robotics on there. Well, let's go take a 10-minute break.